In this presentation we will introduce the basic concepts in the theory of heat, and discuss the first law of thermodynamics and its applications. We start with the clarification of the concept of heat and its relation to the thermal state of bodies and the different forms of energy. Then we introduce the thermodynamic properties of bodies determining the process of heat transfer between bodies. We will see that heat is considered as a form of energy, and one of the most important phenomenon studied in thermodynamics is the conversion of heat into some form of work, especially into mechanical work. When we study thermodynamic processes taking place in bodies and between a group of bodies, we will describe the conversion of heat into mechanical work. When focusing on any process related to the conversion of energy involving the exchange of heat, we will introduce all the fundamental concepts, such as thermodynamic system, state variables or equilibrium. By applying these concepts, we will be able to describe thermodynamic processes in both qualitative and quantitative way. Then we introduce the first law of thermodynamics, formulating the conservation of energy with a simple relation between the change in the energy of bodies, the heat exchanged between bodies, and the work done on or by bodies. In the case of processes taking place in a thermodynamic system, the first law describes the transport of energy through the boundary separating the system from its surroundings. Then the law states that the total energy of the system and its surroundings is conserved, and any thermodynamic process is governed by this principle. The law will also be applied to define new thermodynamic quantities depending only on the state of the system. We also provide the definition of a quasi-static thermodynamic process. If we assume that the deviation of any thermodynamic system from equilibrium is negligible during a process, we can apply a well-defined set of thermodynamic variables describing the state of the system throughout the process. In such a quasi-static process, we can apply the equation of state for the given system without any restriction, which simplifies the analysis of thermodynamic processes. Another important concept discussed here is thermodynamic cycle, describing a cyclic process of the transformation of heat, energy and work in a system. It is a theoretical concept created to study the operational cycles in steam engines, or more generally in heat engines converting heat into work. It is also a fundamental concept for the idealized models of such engines, since it is applied to determine their maximum performance achieved in theory. Finally, we will present an application of the first law of thermodynamics, in the experiment studying the free expansion of an ideal gas. The result of the experiment, together with the consequences of the conservation of energy and the quasi-static approximation of the process, can be used to establish a unique relation between the thermodynamic variables of the gas and its total energy. This relation can be interpreted as an equation of state for an ideal gas, which we will generalize for homogeneous isotropic bodies. If we want to study thermodynamics, that is the theory of heat, we need to start with the concept of heat. Everyday experience indicates that we have to introduce other quantities besides temperature to interpret the phenomena related to warmth in nature. For example, let us begin with a simple observation on the thermal state of bodies. If two bodies with different temperatures brought into thermal contact, then they settle to the same temperature. Let the red square represent a warm body with a temperature T1 and the blue one a cold body with a temperature T2, where T1 is greater than T2. Let us also assume that the two bodies are thermally insulated from their environment, which is represented by the rounded corner rectangle enclosing the symbols of the two bodies. Therefore, these bodies have no thermal contact with their environment or surroundings. If we bring the two bodies into some thermal contact represented by the green rectangle and measure the temperatures of the bodies, then we will see the temperatures change in time. The temperature of the warm body decreases while the temperature of the cold one increases until they reach a common temperature T3. We explain the phenomenon of the temperature equalization by applying the concept of heat, and state that the warmer body becomes colder, transferring some amount of heat to the colder one which in turn becomes warmer. Therefore, the change in the temperature of any object can be explained by the fact that some amount of heat was transported to, or from the object. Once the temperatures of the bodies are equal, the net heat transfer between the two bodies is zero, that is, the objects exchange equal amount of heat among themselves for a given time interval. The following experiments can help us to find out how to measure the amount of heat transferred among bodies and determine the physical unit of heat. We will perform experiments with heating of different fluids, where we assume that the amount of the heat transferred to the fluids is proportional to the duration of heating. Let us pour half a liter of water into a container at 20 degrees Celsius, which is about half a kilogram, and start to warm it. We measure both the temperature of the warming liquid and the duration of heating. When the temperature of the water reaches 25 degrees Celsius, we check the time elapsed from the beginning of heating, which we denote by T. Let Q denote the amount of heat transferred to the water during that time. If we continue the warming of the water until its temperature reaches 30 degrees Celsius, we find that the time of heating is about 2 times T. Since we assume that the transferred heat is proportional to this time interval, the heat absorbed by the liquid is about 2 times Q. If we perform this experiment with 1 kilogram water, we will see that it takes about 2 times longer to warm up the liquid from 20 degrees Celsius to 25 degrees Celsius. Therefore, the amount of the heat transferred to the water is equal to about 2 times Q. When the temperature of water reaches 30 degrees Celsius, we find that the time of heating is about 4 times T. As a result, we can state that the heat absorbed by the liquid is about 4 times Q. If we repeat this experiment with petrol, we find that the time of heating is always about the half of the one measured for water, but the ratios between the measured time intervals remain the same. Therefore, the heat absorbed by the petrol is also the half of the heat absorbed by the water. Other words, it takes twice as long to produce the same amount of increase in the temperature for water than for petrol, which indicates that water needs 2 times more heat to increase its temperature by 5 or 10 degrees than petrol. At the same time, we see that in both cases the absorbed heat is proportional to the temperature difference and the mass of the liquid. We can also conclude from the results obtained for water and petrol that the proportionality factor between heat and mass, or heat and the difference in temperature, depends on the physical properties of the liquid. Then we can talk about 2 cases related to the transport of heat between a body and its environment, warming bodies and cooling ones. A body with mass m and the physical properties characterized by the proportionality factor C at the temperature T1 is warming, if the body absorbs an amount Q of heat and its temperature rises, reaching the temperature T2, where T1 is less than T2. In the case of cooling, the body releases an amount Q of heat and the body is cooled to the temperature T2, where T1 is greater than T2. In order to give a quantitative description of the transport of heat changing the temperature of a body, we can state that the heat Q delivered to a body with mass m is given by the proportionality constant C, times the mass m, times T2 minus T1, if its temperature changes from T1 to T2. We can also say that the amount of heat delta Q exchanged between a body and its environment is proportional to the mass m of the body, times the change delta T in the temperature of the body, where the proportionality factor C depends on the physical properties of the body. Here we always assume that there are no chemical reactions taking place in the process which could release or consume heat. These formulae also show that the delivered heat to a body is negative for cooling. When the initial temperature T1 of the body is greater than its final temperature T2, the body delivers heat to its surroundings. We can draw the same conclusion on the transport of heat from the following experiment mixing different materials with different temperatures. Let us pour water with the temperature 20 degrees Celsius into a container until its mass reaches 100 grams. Let also heat 50 grams water to 80 degrees Celsius, and pour it into the container filled with the cold water. If we mix the cold and the hot water in the container and measure the temperature of the mixture, we see that it goes up to 40 degrees Celsius. Then we can write the following equation for the relation of the products of the mass and the change in the temperature for the cold and hot water. 100 grams times 40 degrees Celsius minus 20 degrees Celsius is equal to 50 grams times 80 degrees Celsius minus 40 degrees Celsius. We can denote the different quantities in this equation with the following letters. The mass of the cold water is denoted by M1, the temperature of the mixture is denoted by T3, the temperature of the cold water is denoted by T1, the mass of the hot water is denoted by M2, the temperature of the hot water is denoted by T2, and again, the temperature of the mixture is denoted by T3. As a result, we obtain the equation stating that the mass M1 times the difference between the temperatures T3 and T1 is equal to the mass M2 times the difference between the temperatures T2 and T3. If we mix water with different masses and initial temperatures and measure the temperature of the mixture, we can demonstrate that this relationship holds for arbitrary masses and initial temperatures. We can also mix different solid materials in water. For example, we take 100 grams water at 20 degrees Celsius again, and we heat up 50 grams iron filings to the temperature 80 degrees Celsius. If we pour the hot iron filings into the container and mix it with the cold water, we can measure the temperature of the mixture. We will see that the temperature in the container is 23 degrees Celsius after mixing. Although we cannot establish the same relationship between the masses and the changes in the temperatures of the water in the iron filings, we still have the following equation. 100 grams times 23 degrees Celsius minus 20 degrees Celsius is proportional to 50 grams times 80 degrees Celsius minus 23 degrees Celsius, where the proportionality constant C depends on the physical properties of the water in the iron filings. In this case the value of C is 0.1. Here we can use the following notations for the quantities in the equation. The mass of the water is denoted by M1, the temperature of the mixture is denoted by T3, the temperature of the cold water is denoted by T1, the mass of the iron filings is denoted by M2, the temperature of the iron filings is denoted by T2, and again, the temperature of the mixture is denoted by T3. We also assume that we can write the proportionality constant as the ratio of a constant C2 to a constant C1, where C1 depends only on the physical properties of the water and C2 depends only on the physical properties of the iron filings. Then we obtain the equation stating that C1 times M1 times T3 minus T1 is equal to C2 times M2 times T2 minus T3. If we change the masses of the water in the container and the iron filings and heat them to various initial temperatures, then we find that the equation still holds. Therefore this relationship gives a general quantitative description of the transport of heat during the mixing of two materials. Here we neglected the heat dissipation over the wall of the container and through the gauge of the thermometer measuring the temperature. We can interpret this result as the water absorbed an amount Q of heat during its warming, where Q is equal to C1 times the mass M1 of the water, times the increased T3 minus T1 in its temperature. Whereas the iron filings release the same amount of heat, which can also be written as C2 times the mass M2 of the iron filings, times the decreased T2 minus T3 in its temperature. Such experiments were performed in 1747 by Georg Wilhelm Richmann, a German physicist, who tried to determine the temperature T3 produced by mixing a quantity of water given by the mass M1 at temperature T1, with another quantity of water given by the mass M2 at temperature T2. The quantitative description of mixing hot and cold water was a well-known problem at that time, and a formula providing the temperature of the mixture was already available. However, there was a discrepancy between the calculations and the result of Richmann's experiments, and he could find a formula confirmed by the results of his measurements. He concluded that the temperature T3 of the mixed water is equal to M1 times T1 plus M2 times T2, divided by M1 plus M2, which is a simple averaging the temperatures weighted by the quantities of water. If we multiply this equation by M1 plus M2 and reorder the terms in the result, we obtain the equation which we have already derived. That is, M1 times T3 minus T1 is equal to M2 times T2 minus T3. We have seen that this relationship can be generalized for mixing of different materials with the formula stating that C1 times M1 times T3 minus T1 is equal to C2 times M2 times T2 minus T3, where we take the physical properties of the mixed materials into account by applying the multiplicative factors C1 and C2. In this experiment, the left-hand side of the equation represents the amount of heat absorbed by the cold water, whereas the right-hand side of the equation represents the amount of heat released by the hot water. In his experiments, Richmann could demonstrate that if two bodies are in thermal contact, then the heat released by the warmer one is equal to the heat absorbed by the colder one, that is, there is an exchange of heat between the two bodies. If a body with the physical properties described by the constant C1 and mass M1 has the temperature T1, and another body with the constant C2 and the mass M2 has the temperature T2, then they will exchange heat in thermal contact. They settle to the same temperature T3, which is given by C1 times M1 times T1 plus C2 times M2 times T2, over C1 times M1 plus C2 times M2, if the two bodies are thermally insulated from their environment, that is, there is no exchange of heat between them and their surroundings. This formula follows from the equation describing the transport of heat between the two bodies thermally insulated from their surroundings. As a result, an important conclusion can be drawn from Richmann's experiments. Heat is conserved in such an insulated system, that is, heat is not created or destroyed but transported within the system. We will see that the conservation of heat is one of the findings which led to the formulation of the first law of thermodynamics. Based on the results of these experiments, we can define the physical unit of heat, and introduce the quantities called specific heat capacity and heat capacity, describing the behavior of bodies related to the change in their thermal state, when they absorb or release heat. We call the physical unit of heat calorie, abbreviated with cal, which is defined as follows. 1 calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Since the physical state of water depends on its temperature and pressure, several definitions of the unit of heat exist. This table shows some of these definitions at different temperatures. Generally, 1 x degrees calorie denoted by cal sub x is the amount of heat required to raise the temperature of 1 gram of water from the minimum temperature Tmin to the maximum temperature Tmax at standard atmospheric pressure. We see that Tmin is 3.5 degrees Celsius and Tmax is 4.5 degrees Celsius in the definition of 4 degrees calorie, that is 4 degrees Celsius is an average temperature of water warmed from the temperature Tmin to the temperature Tmax. Similarly, for 15 degrees calorie the temperatures Tmin and Tmax are 14.5 degrees Celsius and 15.5 degrees Celsius, and for 20 degrees calorie these temperatures are 19.5 degrees Celsius and 20.5 degrees Celsius. There also exists a definition for mean calorie, which uses a broad temperature range, where the minimum temperature is 0 degrees Celsius and the maximum one is 100 degrees Celsius. In the third column of this table we can see the value of 1 calorie sub x divided by 15 degrees calorie, which is maybe the most frequently used definition. This column demonstrates that the definition of calorie depends on the temperature range used for it, since 4 degrees calorie is about 44 thousandths greater than 15 degrees calorie. Similarly, 20 degrees calorie is 84 thousandths smaller and 1 mean calorie is 11 thousandths greater than 15 degrees calorie. When we clarify the relationship between heat and energy we will able to provide an alternative definition of the unit of heat, and these different definitions can be converted into the new unit. By fixing the unit of heat, we can give the proportionality constant C appearing in the equation of heat transfer a unique interpretation. If we express C from the transfer equation of heat, we see that it is equal to the amount Q of heat divided by the mass m times the difference T2 minus T1 of the temperature, or 1 over m, times the ratio of delta Q to delta T. These equations show the following. For a substance with unit mass, the constant C gives the amount of heat needed to increase its temperature with 1 degree Celsius. We have already stated that the value of C depends on the physical properties of materials. When Joseph Black, Scottish physicist and chemist, studied the transfer of heat between bodies, he found that different substances with equal masses need different amounts of heat to increase their temperature with the same amount. Black introduced the concept of specific heat capacity for the proportionality constant between heat and the increase in the temperature of a body with unit mass, which provided a quantitative description of this behavior. For a body with unit mass, specific heat capacity, or simply specific heat, gives the amount of heat needed to increase the temperature of the body with 1 degree Celsius. Generally, if a body with mass m receives the infinitesimal amount dq of heat and increases its temperature with the amount dt, then its specific heat C is 1 over m times the ratio of dq to dt. Therefore, we can interpret the definition of specific heat of a substance with mass m as 1 over m times the derivative of the heat Q absorbed or released by the substance with respect to its temperature T. This equation indicates that the amount of the heat Q exchanged between a body and its environment depends on not only the difference in the temperatures of the body and its surroundings, but also the absolute temperature of the body. The ability of a substance to absorb or release heat clearly depends on its physical properties, which in turn depend on its temperature. As a result, we always treat the heat Q transferred between a body and its environment as a function of its temperature T, and we can determine its heat capacity by differentiating the function Q with respect to T. Its definition shows that the unit of specific heat is simply calorie per gram times degree Celsius. The heat capacity C of a body can also be defined as the product of its mass m and its specific heat C, and it provides the amount of heat needed to increase its temperature with 1 degree Celsius. Then the derivative of the heat Q exchanged by a substance with its surroundings with respect to its temperature T simply gives the heat capacity of the substance. From this definition we see that the unit of heat capacity is calorie divided by degree Celsius. The technique used to measure the heat transferred to or from a substance, or more generally the amount of heat involved in any chemical or physical process, is known as calorimetry. The measurement is performed with a thermally insulated and calibrated device, which we call calorimeter. Since the device is insulated, the heat exchange between the calorimeter and its environment is negligible. Heat flow at constant pressure can be measured by using a constant pressure calorimeter, which allows us to study chemical reactions in mixtures at a constant atmospheric pressure. A simplified version of constant pressure calorimeters is a coffee cup calorimeter. Such an equipment consists of 2 nested styrofoam cups closed with a loose-fitting lid to thermally isolate the solution in the cups from the surroundings, as seen in the figure. The photo shows a more professional apparatus, which is a double-wall calorimeter based on the same principle. A thermometer and a stirrer are placed into the sealed cups or the double-wall container through 2 holes in the lid to measure the temperature and mix the reactants. The principle of the measurement is the following. First we pour distilled water in the calorimeter and measure the initial temperature of the fluid. Then we dissolve reactants in the distilled water and start to mix the solution. As chemical processes take place in the reaction mixture, the temperature of the liquid changes. In the case of exothermic reactions, the reaction produces heat which increases the temperature of the water. When an endothermic reaction occurs, the reaction consumes heat and absorbs it from the solution, decreasing the temperature of the liquid. We can measure the maximum or minimum temperature of the solution and calculate the difference delta T in its temperature by subtracting the initial temperature from this value. Since the volume of the liquid is large, we can assume that the calorimeter absorbs a negligible amount of heat and the specific heat of the solution is the same as the one of the distilled water. Then the amount Q of heat released or absorbed in the experiment is given by the mass m of the liquid, times the specific heat Cp of the water at constant pressure, times the difference delta T of the temperature of the water. The next type of technique is constant volume calorimetry, measuring heat flow in a constant volume. Constant volume calorimetry is used for measuring heat of a particular reaction, especially combustion, where the aim is to determine the calorific value of the fuels. The typical devices applied in constant volume measurements are the bomb calorimeters, which are built in such a way that they can withstand the large pressure produced within the apparatus due to any reaction of the burning fuel. A bomb calorimeter basically consists of enclosed stainless steel can, called bomb, containing the fuel sample with the presence of pure oxygen as seen in the figure. A fully automatized version of such instruments is shown in the photo, including the bomb and the insulated container with a built-in control electronics. The combustion takes place on the pressurized and heavy-walled bomb, which is placed in the container filled with water. The water is stirred continuously to enhance the exchange of heat between the bomb and the liquid. A fuse wire connected to 2 electrodes is kept in contact with the reactants inside the bomb. After the temperature of the apparatus is stabilized, a high voltage is sent across the electrodes and through the fuse wire. The combustible matter is electrically ignited and starts to burn with the presence of pure oxygen. During the combustion kept under a constant volume condition, heat is released by the burning fuel. Since the bomb is in controlled thermal contact with its surroundings, the water absorbs the heat and its temperature rises. The water temperature continues to rise for some time, which can be measured by the thermometer. When it is leveling off and becomes stable, the temperature is recorded together with the initial temperature. The difference delta T between the stable final and initial states gives the measured increase in the temperature of the water. Since the total heat given off in the reaction is equal to the heat gained by the water and the calorimeter, the heat absorbed by the water is given by the mass m of the water, times the specific heat C of the water, times the change delta T in its temperature. The heat gained by the calorimeter is equal to the heat capacity capital C cal of the calorimeter times delta T. If the heat capacity of the bomb calorimeter material, water, and the fuse wire is known, one can calculate the total amount of heat released by combustion of the fuel sample. The third approach presented here is called differential scanning calorimetry, which is used to study endothermic and exothermic transition and determine transformation temperatures in glass transition, melting or crystallization. This technique also enables thermal property and purity analysis, the study of heat history in chemical reactions, and allows one to monitor the variation of the specific heat of materials as a function of temperature. In a traditional calorimeter, a sample is placed in an isolated chamber surrounded by some medium. If a chemical reaction is triggered in the sample, the difference between the temperatures of the sample and the surrounding medium gives information about the heat release and the consumption of the reaction. The differential scanning technique goes further, and uses both a sample and a reference kept under the same conditions and measures the exchange of heat between them and their surroundings. A sample and a reference material are usually in an empty pans or holders which are identical. The figure shows a differential scanning calorimeter, which consists of the sample and reference holder, also called sample unit, the heater with a heat resistor, and the heat sink working with cooling gas, which has enough heat capacity compared to the sample. The lid of the sample holder has a hole to allow the escape of some amount of the sample and its exchange with the surrounding gas if it is vaporized. Heat is supplied into the sample and the reference through the heat sink and the heat resistor of the heater, where the heating has a controlled rate determined by the reference temperature T-ref. Heat flow is proportional to the heat difference of the heat sink and the holders. When endothermic or exothermic phenomena occur in a reaction or transition, heat is compensated by the heat sink. The oven is purged with the sample gas, so that transitions and chemical reactions in different atmospheres can be examined. Different purge gases can also be used in the experiments, for example air providing an oxidative environment, and nitrogen providing an inert environment. This solution helps to identify any decomposition products by oxidation or by internal thermal degradation. In the photo, we can see a differential scanning calorimeter with its control unit in the left-hand side and the thermally insulated container with the sample unit in the right-hand side. In the method of heat flux differential scanning, the temperature difference T-diff between the sample and the reference material is measured as a function of temperature. Another approach is power compensation differential scanning, where the measurement is a dynamic process. When a transition occurs in the sample such as melting or crystallization, the difference of released or absorbed heat is applied to the sample and the reference material per unit time to keep them at the same temperature, while the temperature T-ref of the whole sample unit is varied in a specified program. The difference between the amount of heat supplied to the sample and the reference is proportional to the difference T-diff between their temperatures, which is measured by thermocouples and recorded on the scan as a function of temperature T-ref. By calibrating the standard material, a quantitative measurement for the unknown sample is achievable. A sinusoidal temperature modulation can also be superimposed on the rate of change in temperature, which allows the simultaneous measurement of heat capacity and kinetic effects. This plot shows the difference Q in the heat flux versus the temperature applied to the sample unit, where the differential signal is displayed as a baseline, and a transition, for example solid-solid or glass transition, crystallization and the melting of a metal can be observed as a peak. The area of the peak gives the amount of heat and the direction of the peak indicates the direction of heat flux. For melting and endothermic reactions the peak points downward, whereas for crystallization and exothermic reactions it points upward. After having presented the methods measuring the exchange of heat, we will clarify the relationship between heat and mechanical work. Generation of frictional heat is an everyday experience. For example, rubbing our hands together makes us feel warm, cutting with a circular saw makes its blade hot, and we can also create fire by friction. These examples show the following simple fact. Whenever friction between the surfaces of two moving bodies occurs, heat is released from the bodies. If a force F is acting on a body such that it moves along a straight line covering the distance s on the surface of another body, then the work done on the body is given by the magnitude F of the force times the distance s. This mechanical work is equivalent to the change in the kinetic energy of the body, which we can measure in Joule, that is in kilogram times meter per second squared. At the same time, the friction between the moving surfaces also produce the heat Q which we measure in calorie. Therefore a given amount of mechanical work not only increases the potential and kinetic energy of bodies, but also produces a given amount of heat. Conversely, the example of steam engine, which is an external combustion heat engine that performs mechanical work using steam as its working substance, shows that a given amount of heat can also be converted into mechanical work. The first apparatus demonstrating such a conversion between heat and work is the wind ball or eolipile in Greek, which is a stream reaction turbine. Its invention is usually attributed to Rerum, a mathematician and engineer living in Alexandria, but it was Vitruvius, a Roman architect and military engineer, the first who described an eolipile. The photo shows the reconstruction of the original apparatus, which was a hollow sphere mounted on a pair of hollow tubes so that it could turn on the tubes. The tubes were attached to a sealed cauldron filled with water which was placed over fire. As the water boiled, the hollow tubes provided steam to the sphere from the cauldron. The steam escaped from two bent outlet tubes on the equator of the ball pointing to opposite directions. As a result, the ball rotated about the axis passing through its mounting points, and converted heat into rotary motion. However, this solution was very inefficient at producing usable mechanical work, and the invention was never developed further into an engine applied in everyday life. In the second photo we can see a steam engine, which provided a more effective solution for the conversion of heat into mechanical work in the Industrial Revolution. The principal component of a steam engine is the cylinder with a moving piston, which is connected to a large flywheel. In the first half cycle of its operation, a high-pressure steam flowing into the cylinder pushes the piston out and rotates the flywheel. During the second half of the cycle, the flywheel moves the piston back and pushes the steam through an exhaust valve. Mechanical power is applied during only the first half of the cycle, and the flywheel keeps everything rotating during the second half of the cycle. Although with this solution, the efficiency of steam engines was still much lower than the efficiency of today's engines, their applications radically improved production processes in industry and started a new era in transportation. All these examples demonstrate that heat is a form of energy, and it can be interpreted as thermal energy. Then the conservation of heat, that is, heat cannot be created or destroyed, corresponds to the law of conservation of energy. In fact, the idea that heat is a form of motion is older than the claim of the equivalence of heat and energy. It might date back to ancient times, and Francis Bacon also discussed it in his Novum Organum. The corpuscular theory of matter could help to explore the link between heat and motion as well. Boyle already provided corpuscular explanations for air pressure, and it was the Swiss mathematician and physicist Daniel Bernoulli who formulated a quantitative kinetic theory of gases in his book Hydrodynamica, published 1738. He interpreted gas pressure as the force exerted on a wall of the gas container due to the impacts of particles moving with a given speed in the container. Since the force of each impact is proportional to the momentum of the particles, Bernoulli also showed that pressure is proportional to the kinetic energy of the particles. As a result, his theory introduced the idea that heat or temperature could be identified with the kinetic energy of particles in an ideal gas. In 1760, Mikhail Lomonosov also raised the issue in the framework of corpuscular theory, suggesting that motion can remain hidden in warm bodies due to the extremely small moving constituent particles of matter. However, another explanation of the phenomenon of heat became dominant after Richmond demonstrated the conservation of heat in 1747, which is known as the caloric theory of heat. In this theory, heat was considered as some kind of substance, called caloricum, which cannot be created and destroyed. When Black introduced the concept of specific heat in the interpretation of his experiments performed in 1803, he also refuted the generally accepted claim that heat is proportional to the mass for bodies of equal volume, in other words, to their density. Black was convinced about that his measurements contradicted the kinetic theory of heat, which would imply that the more or the heavier the moving particles are in a body, the greater the amount of heat the body has. Chemistry in that era also seemed to support the idea that heat is a substance. In his explanation of combustion, Lavoisier argued against phlogiston theory, which stated that a combustible substance such as charcoal burned loses weight when it is burned, due to the loss of its phlogiston component to the air. Lavoisier claimed that the phlogiston theory was inconsistent with his experimental results, and proposed a new explanation for combustion in terms of combination with oxygen rather than loss of phlogiston. In 1789, Lavoisier published a list of 32 chemical elements including oxygen, nitrogen and hydrogen. However, the list started with caloricum and he proposed the existence of the subtle fluid of heat, which could help to interpret variety of chemical reactions, like combustion. Caloricum was supposed to be an elastic liquid or fluidum composed by particles repelling each other. At the same time, the particles of the heat fluid are attracted by the particles of ordinary matter, depending on the physical properties and the state of matter. When this substance is present in matter, its particles create bonds with the matter particles which are similar to the chemical bonds. Caloricum can be neither created nor destroyed and it satisfies the conservation law, like ordinary fluids. Although the caloric theory of heat was popular, there was no universal agreement on the weight of the heat substance. Sir Benjamin Thompson, Count Rumford attempted to measure the weight of caloricum, and devised an experiment relying on the balance of equal masses with different heat capacities at a given temperature. In such a setup, different quantities of heat are responsible for equal changes in the temperature of the masses, and an imbalance should result if heat is a substance with mass. However, Rumford found that the amount of heat required to raise an about half a pound gold from the temperature of freezing water to red hot weighted less than a millionth part of the weight of the gold. The result of the measurement demonstrated that even if heat is a substance, it has a negligible weight. The caloric theory also assumed that friction must reduce the heat capacity of the body so that a given quantity of heat substance in the body can raise its temperature. Rumford wanted to examine this effect in the heat generation by friction, and he observed the process of boring cannon barrels. In 1792, he performed an experiment in which he immersed a cannon barrel in water, and used horses to turn specially blunted boring tool at a given rate inside the barrel. The illustration shows the various elements of the apparatus applied in the experiment with the cannon barrel, the boring tool and the container of water. He had observed that the mechanical friction between the tool and the barrel generated heat, which caused the water to boil within roughly 2.5 hours. Rumford established that the amount of heat extracted from the barrel by friction is proportional to time, that is, the supply of frictional heat was seemingly inexhaustible. He also confirmed that the specific heat of the shavings from the barrel remained the same, therefore heat could not released from the barrel as a consequence of the change in its heat capacity. Rumford argued that the seemingly indefinite generation of heat was incompatible with the caloric theory, and so was the fact that the specific heat of the shaving did not change. Then he concluded that one should consider heat not as a substance but as motion. Another important event buried the caloric theory forever. On a cold winter day in London in 1799, Sir Humphry Davy, an English chemist, showed that ice could be melted by rubbing two pieces of ice each other. Since he insulated the pieces of ice to prevent heat exchange between the ice and its surroundings, the heat substance could not flow into the pieces of ice from somewhere else. The heat developed by their mutual friction melt the ice, and it could not arise from any decrease of specific heat in the pieces, because the specific heat of water is greater than that of ice. The only reasonable explanation was that heat was generated by friction, and Davy argued that the immediate cause of the phenomena of heat is motion. As already mentioned, the relationship between motion and heat indicated that heat is a form of energy, and the conversion of energy into heat can be considered as a manifestation of the conservation of energy. The law of conservation of energy was postulated in 1842 by Julius Robert von Meyer, a physician and chemist, who claimed that energy can be neither created or destroyed. This important discovery was also formulated in the concept of mechanical equivalent of heat, stating that energy and heat are mutually interchangeable, and the energy of a system can be changed by either doing work to the system or adding heat to the system. That is, a given amount of work generates the same amount of heat, provided the work done is totally converted to thermal energy. Therefore, the mechanical equivalent of heat is defined as the ratio of the mechanical work converted to heat, to the heat generated by the mechanical work, and it is often denoted by the letter A. We can see from this definition that the unit of the mechanical equivalent of heat is equal to Joule divided by calorie. Meyer calculated the conversion factor between mechanical work and heat, although his result was somewhat different from its real value, due to the inaccurate data used in the calculation. 1 year later, James Joule could demonstrate this equivalence in his famous paddle wheel experiment, and determined the precise value of the mechanical equivalent of heat. First we present Joule's experiment, and then we show how Meyer derived the mechanical equivalent of heat. We start with the measurement of the mechanical equivalent of heat. James Prescott Joule, an English physicist, established that various forms of energy can be converted into another, and in his paddle wheel experiment performed in 1843 he demonstrated that heat and mechanical work are both forms of energy by converting mechanical work into heat. The apparatus used in the experiment can be seen in the figure in the photo, in which a paddle wheel with a string wound around its axis was submerged in an insulated cylindrical vessel of water or mercury. A weight was attached to the other end of the string, which was thrown over a pulley. In the experiment, Joule raised the weight to an appropriate height and dropped it. The falling weight pulled the string, which caused the string to unwind and turn the paddle wheel. The rotating paddles passed through the gaps between a set of fixed vanes in the vessel, producing maximum resistance to the fluid since the motion of the fluid is interfered by the vanes. As a result, the friction between the paddles and the liquid generated heat and raised the temperature of the fluid in the insulated vessel. The weight fell at essentially constant velocity because the frictional force acting on the rotating paddles compensated the acceleration of the moving weight. Joule was able to measure the increasing temperature of the fluid within 1/200 of a degree Fahrenheit, which allowed a precise calculation of the heat generated by friction. He found that the increase in temperature was directly related to the amount of kinetic energy released to the fluid, indicating that an exact relationship governs the conversion of one form of energy into another. In this experiment, Joule could demonstrate that the mechanical work done by the gravitational field could be converted into heat, which was absorbed by the fluid. Since the mass of the weight, the height of the fall and the increase in temperature are given, the mechanical equivalent of heat could be computed as follows. The work W of the gravitational field is given by the product of the weight and the distance of the fall to the floor. If the mass of the weight is denoted by m and h as the distance covered by the falling weight, then the work W is equal to the mass m times the gravitational acceleration g times the height h. However, only the work reduced by the kinetic energy of the weight is converted to heat. Then the heat generated in the fluid is given by the mechanical work W minus the kinetic energy E kin of the weight. If we substitute the work W in the explicit expression of the kinetic energy into the reduced work, we obtain m times g times h, minus 1/2 times m times the square of its velocity v. Here we can factor out the mass m and we have m times the difference of g times h and v squared over 2. Since the insulated vessel was used as a constant pressure calorimeter in the experiment, the heat Q absorbed by the fluid is equal to the product of the heat capacity C of the calorimeter and the increase in the fluid temperature, denoted by delta T. The mechanical equivalent of heat given by the ratio of the reduced work W minus E kin to the heat Q, and A could be written as the ratio of the mass m of the weight to the heat capacity C times delta T, times the difference of gravitational acceleration g times the height h of the fall and the square of the height h divided by 2 times the square of the falling time t of the weight. Here we use the fact that the constant velocity v of the weight is given by the ratio of the height h to the measured time t of the fall. By applying this formula, a numerical relationship can be established between heat and mechanical work. For a given mass m, height h, heat capacity C, and the measured increase delta T in temperature and the time T, Joule could determine the mechanical equivalent of heat. Although in his first measurements he could not yield the value that is considered correct today, with an improvement of the techniques applied in the experiment, he arrived at a value for the mechanical equivalent of heat that is very close to what is in use today. This value is 4.186 Joule per calorie. Nowadays there exist indirect but more precise methods for the measurement of the mechanical equivalent of heat, which use electricity. Now, let us examine how Mayer computed the mechanical equivalent of heat. His method determining its value was essentially the following. If we heat the gas in a container, for example in a cylinder with piston, while its volume is held constant by applying a force F on the piston compensating the increase of the gas pressure, the heat QV absorbed by the warming gas is given by the mass m of the gas, times its specific heat CV at constant volume, times the increase in its temperature denoted by delta T. This process is illustrated in the pressure versus volume diagram of the gas, where the initial pressure P1 is raised to the pressure P2, while its volume V1 remains constant. In the second case, we heat the gas in the cylinder at constant pressure where we let the expanding gas move the piston. The heat QP absorbed by the expanding gas is given by the mass m of the gas, times its specific heat Cp at constant pressure, times the increased delta T in its temperature. This process is illustrated in the pressure versus volume diagram of the gas, where the initial volume V1 of the gas increases to the volume V2, while its pressure P1 remains constant. As the warming gas is expanding, it does work on the piston, where the pressure expansion work W is equal to the pressure P of the gas, times the increase in the volume of the gas denoted by delta V. By comparing the two cases, we can see that the heat QP delivered to the gas at constant pressure is greater than the heat QV absorbed by the gas at constant volume. This surplus of heat is used to supply the pressure expansion work done by the gas, that is W is equal to QP minus QV. If we substitute the expressions obtain the heat QP and the heat QV, we obtain the difference of Cp and Cv, times the mass m, times the temperature difference delta T. The ideal gas law states that the product of the pressure P of the gas and its volume V is equal to the amount N of the gas measured in moles, times the universal gas constant R, times the gas temperature T. Therefore, the pressure expansion work, that is P times delta V, is equal to N times R times delta T. We can insert these results into the mechanic equivalent of heat defined as the ratio of the mechanical work W to the heat Q, which gives N times R times delta T, divided by M times the difference of Cp and Cv, times delta T. After simplifying this expression, we obtain N times R over M times the difference of Cp and Cv. Since the product of the mass m of the gas and its specific heat gives the heat capacity of the given amount of gas, we can write the mechanical equivalent of heat as the ratio of N times R to the difference of the heat capacities of the ideal gas measured at constant pressure and in constant volume. If the heat capacities are known, this expression can be used to determine the value of the mechanical equivalent of heat. If we multiply this equation by capital Cp minus capital Cv, we can see that A times the difference of capital Cp and capital Cv is equal to N times R. We can divide this equation of the amount of substance N, and introduce the molar heat capacity capital Cm of the substance defined as its heat capacity C over the amount of substance N. Then we have the following equation. The mechanical equivalent of heat A times the molar heat capacity capital Cpm of the gas measured at constant pressure minus the molar heat capacity Cvm of the gas measured in constant volume is equal to the universal gas constant R. Although we have measured heat in calories, we can follow the convention of measuring both heat and work in the same units, namely in joules. Then by definition, the mechanical equivalent of heat is equal to 1, and we obtain Mayer's relation stating that the molar heat capacity capital Cpm of the ideal gas measured at constant pressure minus the molar heat capacity Cvm of the ideal gas measured in constant volume is equal to the universal gas constant R. As already mentioned in the presentation of the ideal gas laws, the gas constant R in the right-hand side of the equation is equal to 8.314 Joule per mole Kelvin. Since we have clarified the concept of heat used in thermodynamics, we can introduce the term thermodynamic system, considered as a starting point in the study of heat. Roughly speaking, we will call the physical object of interest a thermodynamic system if we study thermodynamic processes related to the object, such as the transport of heat and energy and the conversion from one form of energy to another one. The birth of the concept of thermodynamic system can be dated back to the activity of Nicolas Léonard Sadi Carnot, a French mechanical engineer who studied steam engines and tried to improve their performance. We have already seen that steam engines are able to do work when heat is applied to them. That is, a high-pressure steam is generated in such machines, which flows into a cylinder and pushes a piston transforming heat to motion. In his book published in 1824, Carnot defined a theoretical heat engine shown in the cross-sectional diagram, where the points from A to G denote a cylindrical vessel, the points C and D denote a movable piston, and the capital A and B are bodies of constant temperature. Carnot called the body of water vapor substance employee or substance mise en oeuvre, translated as working substance. The term work indicated that the steam does the mechanical work in the cylinder by moving the piston, which could be put in contact with either a heat reservoir, for example a boiler, or a cold reservoir, for example a stream of cold water. In this context, the working substance, the cylinder with the piston and the reservoirs can be considered as the components of a thermodynamic system. In 1850, Rudolf Clausius, a German physicist and mathematician, went further when he introduced the term der Werksumkörper or working body to describe such a system, and he included the concept of surroundings in the description. That helped in the study of the heat and energy transport between a heat engine and its environment, handled as a whole. As a result, the law of conservation of mass and energy could consistently applied in the form of balance equations for mass and energy describing the cyclic process converting heat to mechanical work. In 1878, Josiah Willard Gibbs, an American scientist, analyzed heterogeneous systems formed by a body or collections of bodies that can be solid, liquid, gas, or some combination of these states. He called these systems material system, and this concept could already be regarded as the generalization of any physical system, where the transport of mass, energy and heat was studied together with phase transitions and chemical reactions. Towards the end of the 19th century, the term thermodynamic system was already established, and nowadays we use this concept to describe and study any phenomenon related to heat and introduce the laws of thermodynamics. The basic ideas appearing in these historical remarks can help us to introduce the modern concept of thermodynamic system and describe its fundamental properties. A certain quantity of matter located in some spatial volume is considered as a thermodynamic system, where the region outside the system is called surroundings. The system and the surroundings are separated by a boundary. In thermodynamics, we study the exchange of heat, work and other forms of energy among the material objects and spatial volumes within the system, and between the system and its surroundings. We have already seen that Gibbs studied collections of bodies which were solid, liquid, gas, or some combination of these states. Such a description applying the state of matter shows that we can classify thermodynamic systems based on the macroscopic properties of regions within them. If we define the concept of phase as a homogeneous, physically distinct, and mechanically separable portion of a system, then this classification becomes simple. In this respect we deal with two types of systems, homogeneous thermodynamic systems and heterogeneous ones. A homogeneous system is a single-phase system, that is, the system is made of one phase only. In other words, a homogeneous thermodynamic system is defined as the one whose chemical composition and physical properties are the same throughout the entire system, or change continuously from one point to another. A simple example for a homogeneous system is a gas enclosed in a given volume, like these airbags in the photo. Here both the chemical composition and the phase of the substance filling the closed volume is the same the whole gas. Liquids are also considered as homogeneous systems. The photo shows a colored fluid in a flask, demonstrating that a liquid still takes the shape of the container but it does not fill every space in it. Nevertheless, we can only see one phase in the system and the chemical composition is uniform throughout its volume. A further example for homogeneous systems is a solid of a given material, like the block of copper in the photo, which has the same chemical composition in the entire body. In thermodynamics, we can study the transport of heat or other forms of energy in these relatively simple systems or in the interaction with their environment. A heterogeneous thermodynamic system consists of two or more phases. In such a system, each phase is separated from other phases by interfaces, where the chemical composition of the substance or its physical properties abruptly change. An example for a simple heterogeneous system is a two-component fluid, where the components of different density are separated from each other. In the photo, some oil is poured into a glass of water which do not form a mixture but the oil emerges on the surface of the water. Ice floating in water is also a heterogeneous system where fluid and solid phases of the same substance coexist in separation. The last example for a heterogeneous system is a solid body or a collection of solid bodies, where the parts of the body or the members of the collections are composed of different materials. The photo showing some grains of sand demonstrates how different the physical properties of the individual parts of such a system can be. As opposed to the phase interfaces considered as simple thin layers in heterogeneous systems, the boundary between a thermodynamic system and its surroundings can have different fundamental properties, which determines the transport processes through the wall representing the boundary. We distinguish between three different types of transport through walls: the transport of mass, the transport of energy, and the transport of momentum. Based on this distinction, we compiled this table containing all the possible types of walls applied in thermodynamics. If the transport of mass is allowed through the wall, then we talk about a permeable wall, otherwise the wall is impermeable. An example for permeable walls is the double layers of the wall and the plasma membrane of a cell. The wall is fully permeable to most molecules, but the membrane of selective permeability helps to concentrate certain dissolved molecules and ions inside the cell. The study of the transformation of energy in thermal and electrochemical processes and transports occurring across this permeable wall membrane structure is an important application of thermodynamics. A typical example for impermeable walls is the wall of a gas cylinder, which prevents the gas in the cylinder from escaping. In thermodynamics, we can consider any substance, gaseous or liquid, enclosed some container, and study the exchange of heat between the substance and the environment while it remains confined within the impermeable walls of the container. If the transport of energy is allowed through the wall, normally in the form of heat transfer, the wall is called a diathermal wall. If the transport of energy is forbidden, that is, the wall is a perfect thermal insulator, then we talk about an adiabatic wall. Pressure cookers have a diathermal wall made of aluminum or stainless steel, which are excellent heat conductors. If we place a pressure cooker on the top of a stove, then it takes 5 to 30 minutes to heat up any food or water in the cooker, indicating an extensive heat transfer through the wall of the cooker. The function of a Dewar flask or a thermos bottle is the opposite. It prevents the exchange of heat through its adiabatic wall. Such a vessel keeps its content hotter or cooler than the environment, since the evacuated region in its wall provides thermal insulation between the content and the environment. If a wall can be moved, then it allows the transfer of momentum between the system and its surroundings, whereas fixed walls do not allow such a transfer. We can find both movable and fixed walls in an engine. If we consider the fuel combusted in each cylinder of the engine as a system, then the piston moving in the cylinder is the movable wall of the system and the cylinder represents its fixed wall. As illustrated by the pair of a cylinder and a piston, the boundary of a thermodynamic system can be a collection of different types of walls. If we classify thermodynamic systems based on the types of walls surrounding them, we can talk about 4 different types of systems which are shown in this table. The first type of thermodynamic system is the isolated system, which is separated by an impermeable, adiabatic and fixed wall from its surroundings. Such a wall prevents the exchange of mass, energy and momentum between the thermodynamic system and its surroundings, isolating the system completely from its environment. Since the wall of any Dewar flask has an impermeable, adiabatic and fixed wall, any substance stored in such containers can be considered as an isolated thermodynamic system. The second type of thermodynamic system is the adiabatic system, which is separated by an impermeable, adiabatic, and moving wall from its surroundings. An adiabatic system can exchange work with its surrounding by the momentum transfer through its moving wall. At the same time, the wall prevents any exchange of mass and energy. A typical example for an adiabatic system is an insulated cylinder filled with gas and closed by a piston, provided the transport of heat through the wall of the cylinder and the friction of the moving piston can be neglected. If the moving piston increases the volume of the gas, then we talk about an adiabatic expansion of the gas, where the gas cools down since it cannot absorb heat from its surroundings. The third type of thermodynamic system is the closed system, which is separated by an impermeable, diathermal, and fixed wall from its surroundings. An energy transfer in the form of heat exchange is possible between a closed system and its environment, but any transport of mass and momentum is prevented by the boundary. An obvious example for a closed system is the food or water enclosed in the pressure cooker. The metal wall of the cooker allows the transport of heat from the oven to inside the cooker without exchanging any mass or work. The last type of thermodynamic system is the open system, which has no wall and the transfer of any quantity is allowed between the system and its surrounding. One can interpret such a system as we draw only a hypothetical boundary between the system and its surroundings. If we open the valve of a gas cylinder, or remove the lid of the pressure cooker or the cap of the thermos, all the substance held in these containers become open systems, where the exchange of mass, energy and momentum is free. Since we have introduced the concept of thermodynamic system, we can define the state of such a system, also known as thermodynamic state. In the discussion of the combined gas law, we saw that the law determines the temperature and the pressure of a given amount of ideal gas enclosed in a volume. Therefore, the physical state of an ideal gas is uniquely described by its pressure, volume, and temperature, and we can measure all of them. In general, experimentally measurable macroscopic properties describing the state of a thermodynamic system, such as mass, volume, pressure, temperature, gravitational or electric field and so on, are called thermodynamic parameters or state variables. In the case of an ideal gas, the state variables uniquely describing the thermodynamic state of the gas with a given mass m or given amount of substance n consist of the pressure P, the volume V, and the temperature T of the gas. Although the mass and the amount of species of the gas are also state variables, they can be considered as fixed parameters if the gas is enclosed in a container with an impermeable wall. In such a case, the mass or the amount of species does not change in the system and the state variables pressure, volume, and temperature are enough to describe the state of the gas. In general, if n physical quantities describing the macroscopic properties of a thermodynamic system, denoted by x1, x2, ellipsis, xn, are necessary to uniquely define the state of the system, then we call these quantities thermodynamic parameters or state variables. The thermodynamic state of a system is uniquely determined by a given set of state variables. As a result, we can represent the state of the system with a point in an n-dimensional space spanned by the set of the thermodynamic parameters. Since the state variables for a given amount of ideal gas are its temperature, pressure, and volume, we can plot a three-dimensional Cartesian coordinate system with the axes for these quantities. In this coordinate system, the point P represents a given set of the temperature T, the pressure P, and the volume V describing the thermodynamic state of a given amount of ideal gas. In the general case, we can use the n-dimensional coordinate space for the state variables x1, x2, ellipsis, xn, where the point P represents a given set of the values of the thermodynamic parameters. The variables x1, x2, ellipsis, xn are called the generalized coordinates of the thermodynamic system, and the vector with these coordinates describes the thermodynamic state of the system. If we classify the state variables of a system based on their relationship with the surroundings, we can talk about external and internal state variables. External state variables only depend on the generalized coordinates of external bodies interacting with the system which belong to the surroundings. For example, the volume V of a gas in a closed space is an external state variable, determined by the geometric configuration of its boundary and the surroundings. Similarly, any external force acting on the system, like the force F holding the piston at a fixed position or moving it, or the gravity acting on the gas in the container, is also an external state variable. Internal state variables depend on the generalized coordinates of both internal and external bodies. The pressure of a given amount of gas depends on both its temperature and volume, where the temperature is another internal state variable and the volume is determined by external parameters. Therefore, the pressure is an internal state variable determined by both internal and external coordinates. We have seen that the state of a thermodynamic system can be determined at a given instant of time by specifying a set of state variables describing the state uniquely. However, we have not examined whether this instantaneous state is temporary or permanent. That is, whether the thermodynamic state of a system is changing in time or remains the same. From this point of view, we can talk about a special situation. If a system is in a stationary thermodynamic state, then the state of the system is independent of time. In other words, the physical properties of the system do not change with time, and the generalized coordinates x1, x2, ellipsis, xn specifying the instantaneous state of a thermodynamic system are constant. The relationship between the state of a system and the transport processes between it and its surroundings is complex. Even if the transport of mass, energy, or momentum is prevented between the system and its environment, it does not follow that the system is necessarily in a stationary state. For example, any exothermic chemical reaction in an insulated thermodynamic system releasing heat and changing the chemical composition within the system, modifies its state. Inversely, a thermodynamic system exchanging mass, energy, and momentum in the form of work with its environment can still be in a stationary state. That is, a mass or a heat flow between a steady-state system and its surroundings does not necessarily change its physical properties with time. If the point P represents the steady state in the n-dimensional state space, then the vector x constructed from the generalized coordinates of the system is a constant vector. As a result, the steady-state system will never leave this point during its time evolution, and the trajectory of such a system is only the point P representing its initial state in the state space. We can distinguish between different aspects of the thermodynamic state, talking about the thermal, mechanical and chemical properties of the system. If a thermodynamic system is in a steady state, then the system is also in a steady thermal state, and its temperature is constant. A steady state system is in a steady mechanical state as well. For example, it has a constant volume, and it is also in a steady chemical state, where its chemical composition does not change, that is, the amounts of various species remain the same with time in the system. An everyday example for stationary thermodynamic state is the operation of an air conditioning system. As the photo shows, the air conditioner is installed on the wall of a building. The device has three main components: an evaporator, a condenser, and a compressor. The compressor is circulating the air between the evaporator inside the air conditioner, and the condenser is located outside the building. The air conditioner pulls warm air through air vents in the building and coil it in the evaporator filled with a gaseous refrigerant to absorb heat. The warm refrigerant is pumped outdoors to the condenser so that the heat can be released. The refrigerant leaves the evaporator in the form of a warm, low-pressure gas. In order to release the heat absorbed by the refrigerant, the gas needs to have higher temperature and pressure. The compressor reduces the volume of the gas to add pressure and increase temperature. The heat moves from the high-temperature refrigerant to the cooler outdoors, where it can be released through the condenser, turning the pressurized gas into liquid vapor. Then the refrigerant travels back to the evaporator, where the process begins again. In a steady operation of the air conditioner, the indoor temperature is held constant and the air inside the building remains in a steady state. In general, the effect of any process releasing heat in a thermodynamic system can be compensated by circulating some coolant between the system and its surroundings, which keeps the system at the same temperature. The steady transport of mass and energy between the system and its environment allows one to hold the system in a stationary state. In this example, we have seen an interaction between the system and the surroundings causing the state of the thermodynamic system to be independent of time. However, external processes are not always necessary to prevent the system from changing its thermodynamic state, which is formulated in the following concept. Thermodynamic equilibrium is the condition or the state of a thermodynamic system, where the properties of the system do not change with time, and no external processes take place in maintaining the state of the system. In equilibrium, the generalized coordinates x1, x2, ellipsis, xn describing the state of the system are constant in time, as in the case of the stationary state. Since macroscopic change does not occur in the thermodynamic system and no external processes maintain this state, the net macroscopic flows of mass, energy, and momentum in the system, and between the system and its surroundings cease to exist. As a result, if a thermodynamic system is in equilibrium, then it is in thermal, mechanical and chemical equilibrium at the same time, which has no tendency for spontaneous change. We have seen that one of the criteria for thermodynamic equilibrium is that the net exchange of mass, energy and momentum is zero between the system and its surroundings. In fact, such a condition can be met both in isolated and open thermodynamic systems. If we wait long enough, then any flux of mass or heat diminishes and any chemical transformation stops in an isolated system. Since the transport of mass, energy, and momentum is forbidden through the boundary, no spontaneous change takes place in the system after it reached its equilibrium, and it remains in that state. In the case of an open system, the exchange of mass, energy and momentum is free between the system and its surroundings. Normally, we can regard the surroundings as a heat bath and a reservoir of various motionless substances. After the open system has equalized its temperature, pressure, and matter content with those of the surroundings via mass and heat transport, the transport processes will stop and the physical properties remain the same in the system. Therefore, the open system can also reach equilibrium and remain in balance with its surroundings. These two cases can be demonstrated with a Dewar flask or thermos. If we fill the flask with any substance at a given temperature and close it, then its impermeable and adiabatic fixed wall will prevent any transport between the substance in the flask and the environment. As a result, the substance is in equilibrium and remains in the same state until we remove the cap of the flask. Then the substance can exchange heat with its surroundings and mix with it, depending whether it is a gas or fluid. After equalizing its temperature with that of the surroundings, the substance will reach its equilibrium in the open flask. When we discuss the ideal gas law, we considered the functional relationship between the state variables of the gas given by the law as the equation of state for ideal gas. We saw that the state variables of the gas are its mass or amount of substance, together with the pressure, the volume, and the temperature of the gas. The ideal gas law formulates a unique relationship between the state variables of n mole ideal gas confined in the volume V at the pressure P and the temperature T, which states that the product of the pressure P and the volume V is equal to the amount N of the substance, times the gas constant R, times the absolute temperature T. In many cases thermodynamic processes are studied for a given amount of ideal gas, where the amount N of substance or the mass of the ideal gas is constant. Then we have three state variables in the ideal gas law while the amount of substance is held fixed, and the equation of state for ideal gas establishes a unique functional relationship between these state variables, that is the pressure, volume, and temperature measured in thermodynamic equilibrium. The function f depending on the state variables pressure P, volume V, and temperature T for a given amount of substance is equal to 0, where f is given by P times V, minus N times R times T. We have already shown the plot of this functional relationship in the pressure, volume, and temperature diagram, when we derived and studied the ideal gas law. This functional relationship is represented by a surface in this three-dimensional space, where the function f is equal to 0. The equation of state confines the possible states of an ideal gas on the surface in the state space spanned by the thermodynamic parameters pressure, volume and temperature. That is, the thermodynamic state of an ideal gas is always represented by a point on this surface. In any thermodynamic process, the initial and final states of an ideal gas are always on this surface, provided both of them are thermodynamic equilibrium. The intersection curves of the planes of constant temperature in this surface are represented by the red curves for the temperatures T1, T2, and T3. Similarly, the blue lines represent the intersections of the planes of constant volume for V1, V2, and V3, and the surface, whereas the green lines represent the intersections of the planes of constant pressure for P1, P2, and P3 in the surface. This figure demonstrates that by fixing two of the state variables, we can determine the third one from the intersection of the planes of constant for the fixed state variables and the surface of the function f. That is, from the equation of state we can determine the pressure of an ideal gas enclosed in a given volume at a given temperature. For example, if the volume and the temperature of the gas are equal to V3 and T3 respectively, then the intersection of the curves V3 and T3 on the surface gives the gas pressure, which is equal to P3. Similarly, if the pressure and the temperature of an ideal gas are given, then the equation of state tells us the volume in which it is confined, and by fixing the pressure of an ideal gas enclosed in a given volume, we can also determine the gas temperature from the equation of state. Based on these considerations on the ideal gas, we can define the equation of state for general case. The equation of state is a fundamental characteristic of substances and describes the state of matter of a substance under a given set of physical conditions. The equation of state is used to characterize gases, fluids, fluid mixtures and solids, and it reflects atomic structure, chemical bonding and stability of a material. The equation of state of a thermodynamic system is a functional relation between the state variables x1, x2, ellipsis, xn in thermodynamic equilibrium, written as some function f depending on these variables which is equal to 0. In fact, equations of state are derived by applying thermodynamic relations between the state variables, together with either experimental measurements or theoretical calculations based on the methods of statistical physics, using various models of interactions between particles in a system. If the equation of state of a thermodynamic system is given, then it can be represented by an n-1 dimensional hypersurface in the n-dimensional state space. This hypersurface can be considered as a constraint surface for the thermodynamic states of the system, that is, its any possible state lies on this hypersurface. As already mentioned, the constraint surface describes only thermodynamic equilibrium. If the initial and the final states of a thermodynamic system are equilibrium states, then the points representing these states are on the hypersurface. However, the changing states of a system in a thermodynamic process are not necessarily confined on the hypersurface. Such non-equilibrium situations are studied in non-equilibrium thermodynamics, and the equation of states for such scenarios are derived by applying non-equilibrium methods in statistical mechanics. When we discussed the concept of heat, we talked about the assumption that heat is a form of energy, which throws a new light upon the role of the frictional forces in mechanics. It is a well-known fact that the law of conservation of mechanical energy does not hold, if frictional forces also act in the system. For example, in the case of a body sliding on a slope with friction, or in Joule's paddle wheel experiment, the mechanical energy of the system, that is the sum of the potential and the kinetic energy, continuously diminishes, while friction generates so much heat that the sum of mechanical and thermal energy is conversed. There exist numerous physical quantities besides the mechanical and thermal energy, which can also be interpreted as some form of energy. For example, we can talk about electromagnetic and chemical energy, the energy of photons and the energy of nuclear forces. In the discussion on the concept of heat, we mentioned that the law of conservation of energy was postulated in 1842 by Julius Robert von Meyer. He studied how different forms of forces, as he called energy, were converted into each other. From his clinical observation he concluded that the color of blood indicates higher oxygen consumption, which helps to maintain body temperature. He realized that in this process life-sustaining heat is provided by nature, and interpreted it as the transformation of energy, where energy is conserved. He concluded that energy can be neither created or destroyed, and suggested various experiments to examine the transformation of energy into heat. We have already discussed the paddle wheel experiment performed by Joule in 1843, where he determined the mechanical equivalent of heat, demonstrating the transformation of mechanical energy into heat. The result of his measurement provided the first experimental value of the mechanical equivalent of heat, which was a quantitative description of the transformation process between mechanical energy and heat. Experience also shows that the conservation of the sum of the mechanical and thermal energy in the example of a body sliding on a slope with friction or in the paddle wheel experiment can be generalized. Hermann Ludwig von Helmholtz formulated the law of conservation of energy as a generally valid principle in his paper from 1847. The acceptance of the principle in modern physics stems from this publication. He considered work and heat of various forms of natural force or energy in modern terminology. The particularly clear and simple formulation of the law of conservation goes back to Helmholtz, and states that energy can neither be created nor destroyed. Energy can only be transformed from one form to other forms or transferred from one body to other bodies. He also concluded from the conservation of energy that the total amount of energy remains unchanged in the whole universe, considering it as an isolated system. We have seen that the law of conservation of energy in its general form states that energy can neither be created nor destroyed, but can only be transformed from one form to other forms. Since this law is one of the fundamental laws in the theory of heat, it is called the first law of thermodynamics. We also know that an isolated thermodynamic system has no exchange of mass, energy and momentum with its surroundings, since the boundary separating them from each other consists of an impermeable, adiabatic and fixed wall. Since the transport of mass, energy and momentum is not possible through the wall, energy cannot leave the system in the form of heat, or it cannot be absorbed from the surroundings. At the same time, the law of conservation of energy claims that energy can neither be created nor destroyed, but it can transform from one form to other forms in the system. Therefore, the total energy of an isolated system is conserved, which is another formulation of the law of conservation of energy or the first law of thermodynamics. We can talk about a non-isolated thermodynamic system as well, where the flux of mass or heat is possible between the system and its surrounding through a permeable and diathermal wall, or work can be done by the system on the surroundings or on the system by the moving wall operated from the surroundings. Since the law of conservation tells us that energy cannot be created or destroyed in a system, any change in its energy can only be attributed to the exchange of heat or to the work done by or on the system. As a result, we can also formulate the first law of thermodynamics in the following form. The change in the total energy of a non-isolated system is equal to the sum of all the heat transported to or from the system, and the work done by or on the system. For example, if a thermodynamic system does work on its surroundings, then its energy will decrease by the same amount. Therefore, it is impossible to construct a machine or engine which is able to do work without consuming the same amount of energy. If such a machine existed and was set in operation or motion, it would continue to do useful work without an external source of energy, or produce more energy than it was absorbed by a cycle of its operation. Once the machine is started, it would run forever, and the machine would perform a perpetual motion. The mechanism producing such a motion is known as perpetual motion machine, or perpetuum mobile of the first kind. Strictly speaking, perpetual motion machine is a device whose parts are not only in permanent motion, but moreover is able to provide useful work or produce energy without input of external energy and without change of the physical or chemical states of its parts. For example, if En denotes the energy transferred from the surroundings to the perpetuum mobile, and the machine either does the work W or produces the energy E out, or both, then the input energy En is less than the sum of the work W and the output energy E out, while the internal state of the machine does not change. Such a mechanism violates the principle of conservation of energy. Then another formulation of the first law of thermodynamics tells us that a perpetuum mobile of the first kind cannot exist. Since the first law of thermodynamics postulates the conservation of energy in a thermodynamics system, it allows us to introduce the concept of internal energy of such systems. Here we define internal energy in a system undergoing a thermodynamic process. Let us consider a thermodynamic system in a given thermodynamic state denoted by the label 1. Let us also suppose that the system absorbs a given amount of heat from its surroundings, and a given amount of work is done on the system by the surroundings, denoted by Q and W respectively. The general assumption on the surroundings is that the exchange of matter, energy, and momentum between the system and its surroundings never changes the thermodynamic parameters of the surrounding. For example, the absorption or release of heat by the surroundings will not change its temperature, that is, the surroundings behave as a thermal reservoir or a heat bath. Similarly, an arbitrary amount of work can be done on the system by the surroundings, or on the surroundings by the system without changing the surroundings. After the thermodynamic system has reached equilibrium, its physical conditions can be represented by the final state too. For example, if the thermodynamic system is an ideal gas enclosed in a cylinder with a diathermal wall and a movable piston, we can describe the state of the system with the pressure P1, the volume V1 and the temperature T1 of the gas. Then the cylinder is brought in contact with a heat bath with a temperature THB which higher than that of the gas, and the gas also compressed in the cylinder by moving the piston. As a result, the thermodynamic parameters of the system will change to P2, V2 and T2, that is, the heat absorbed by the system and the work done on the system change its state. The temperature of the gas reaches the temperature of the heat bath, and its volume becomes smaller after the compression. We can also denote the total energy of the system in the initial state 1 and the final state 2 by E1 and E2 respectively. Now we can apply the first law of thermodynamics, which states that the change of the total energy in the system is equal to the sum of the heat absorbed by the system and the work done on the system. That is delta E, defined as E2 minus E1, is equal to Q plus W. Since we transferred energy to the system in the form of heat and work, the total energy E2 of the system in the final state is greater than its total energy E1 in the initial state. Thus the sum of the heat Q and the work W is greater than 0. In fact, if a thermodynamic system is in equilibrium, then its total energy E is given by the sum of its kinetic energy E kin, its potential energy E pot, and the internal energy of the system denoted by U. The internal energy U characterizes the microscopic motion within the thermodynamic system. In the case of an ideal gas, the internal energy of the gas is related to the microscopic motion of the gas particles. In the molecular theory of heat, any gas consists of particles in the state of a constant random motion. The theory shows that the warmer the gas is, the more intensive the thermal motion of the gas particles becomes. Therefore, the thermal velocity or speed of these particles is proportional to the temperature of the gas. Since we can associate the internal energy of the gas with the average speed of the particles performing thermal motion, the internal energy U of an ideal gas is proportional to its absolute temperature T, or more generally, the change delta U in the internal energy of an ideal gas is proportional to the change delta T in its absolute temperature. If a gas absorbs heat or is compressed, its temperature increases and the change in its internal energy is positive. Let us suppose that the thermodynamic system is at rest with respect to the frame of reference attached to the laboratory where we study the system. Then the kinetic energy of the system vanishes and its potential energy is constant. Therefore, the difference in the total energy of the system in the state 2 and the state 1 reduces to the difference of its internal energy in those states. As a result, the first law of thermodynamics states that the change of the internal energy of the system is given by the sum of the heat absorbed by the system and the work done on the system, that is delta U, defined by U2 minus U1, is equal to the heat Q plus the work W. We always follow the sign convention according to which the heat absorbed by the system and the work done on the system are positive, whereas the heat released by the system and the work done by the system are negative. Then the heat absorbed by the ideal gas from the heat bath and the work done on the gas by the moving piston increase the internal energy of the system. As a result, the heat Q and the work W are positive, and the change delta U of the internal energy of the gas is also positive. Now we can introduce the concept of state function, which describes an important property of the internal energy of a thermodynamic system. We have seen that the internal energy of the system has a unique value in the initial state 1, and another unique value in the final state 2. We also know that the thermodynamic state of a system is completely described by a given set of state variables, let us say x1, x2, xn. That is, the point P in the state space with the coordinates given by the state vector x characterizes the state of the system in equilibrium. Therefore, the internal energy of the system is a unique function of the state variables or the state vector x, and we can call internal energy a state function. In general, we define a state function f as a unique function of the thermodynamic state of the system, that is a function completely determined by the state variables or the state vector of the system. We have already seen that the pressure P, the volume V and the temperature T of a given amount of ideal gas form the full set of its state variables. Since the ideal gas law provides a functional relation between the three state variables, it is enough to specify two of them to determine the thermodynamic state of the gas. For example, by fixing the volume V and the temperature T of the ideal gas we determine its state, and its internal energy is a unique function of the volume and the temperature. Then in the initial state 1 of an ideal gas before its heating and compression, its internal energy U1 is a function of its initial volume V1 and its initial temperature T1. Similarly, in its final state 2 after its heating and compression, the internal energy U2 of the gas is a function of its final volume V2 and its final temperature T2. As a result, the first law of thermodynamics can also be interpreted by using the concept of state function. If a thermodynamic system evolves from its initial state 1 to its final state 2, while it exchanges the heat Q with its surroundings and the work W is done by or on the system, we can state the following. The change in its internal energy U, which is the sum of the heat Q and the work W, only depends on the initial and the final states of the system, and is independent of the path along which the system evolved from the state 1 to the state 2 in the state space. When considered separately, the heat Q and the work W generally depend on the path of the thermodynamic process. Therefore they are not state functions. In the case of the ideal gas, the heat Q absorbed by the gas and the work W done on the gas depend on both the initial and the final volumes and the temperatures of the gas, and the path calligraphic P connecting its initial and final state. If we choose another path between the two states, then we do not necessarily need the original amount of heat or work to bring the system from the state 1 to the state 2. Only the sum of the heat Q and the work W remains the same, since it gives the change in the internal energy of the system which solely depends on its initial and final state. In the discussion of the first law of thermodynamics, we talked about the work done on a thermodynamic system by its surroundings, when external forces act on the system. Such external forces can include mechanical, electromagnetic, and other type of forces. Now we study the work done by changing the volume of a thermodynamic system, that is when mechanical forces expand or compress the substance in the system. In the example illustrating the first law, the piston compressing or expanding an ideal gas in a cylinder did work on the system. A thermodynamic system can also do work on its surroundings. For example, if the ideal gas expands or contracts in a cylinder, then the gas does mechanical work by moving the piston. In any thermodynamic process, where a substance in the system changes its volume, the work done either on or by the system is called pressure-volume work. The explicit expression of the pressure-volume work can be easily derived for a volume of a rectangular cuboid due to its simple geometry. Let us consider a given amount of compressible substance, and choose a region with the shape of a rectangular cuboid in the space filled by this substance. For a given length A, width B, and height C, volume V of the region is simply equal to A times B times C. Let also suppose that the pressure is P throughout the substance, and the pressure forces acting on the faces of the region compress the substance in it. Due to the compression, the volume of the substance will shrink and occupies a smaller rectangular volume with the length A minus delta A, the width B minus delta B, and the height C minus delta C. If we want to determine the pressure-volume work done by the pressure forces, we have to calculate the work done on the individual faces of the region containing the substance. Let us start with the top and bottom faces of the rectangular cuboid. We denote the forces acting on these faces by F with the subscript TB, which means top and bottom faces. If we apply the definition of pressure, these forces are given by the product of the pressure P in the area ATB of the top and bottom faces, where the face area is equal to the length A times the width B. These forces do work on the substance when they compress its volume along the vertical direction. The work calculated for the top or the bottom faces is equal to the product of the force FTB acting on the faces and the distance STB, along which the faces move in the vertical direction due to the shrinking of the volume of the cuboid. The distance STB is equal to the change delta C in the height divided by 2. The total work WTB for both faces is given by 2 times FTB times STB, which can be written as 2 times P times A times B, times delta C divided by 2. Then the work WTB is given by the pressure P, times the length A, times the width B, times the change delta C in the height. The total work W done by moving all the 6 faces can be written as the sum of the work WTB done on the top and bottom faces, the work WLR done on the left and right faces, and the work WFB done on the frontal and back faces of the cuboid. Since the work done on the left and right faces, and on the frontal and back ones can be expressed in the same way as the work done on the top and bottom faces, the pressure volume work W is given by P times the quantity of A times B times delta C, plus A times C times delta B, plus B times C times delta A. We can also express the change delta V in the volume as the difference between the final volume and the initial volume of the region after and before the compression of the substance. That is, delta V is equal to A minus delta A, times B minus delta B, times C minus delta C, minus A times B times C. If we multiply the terms in the parentheses and reorder them, we obtain A times B times C, minus the terms first order in the change of the linear size of the cuboid, plus the term second order in the change of the linear size of the cuboid, minus the term third order in the change of the linear size of the cuboid, minus A times B times C. Here the first and the last term cancel each other out, and only those terms remain which contains delta A, delta B or delta C. If we assume that the changes delta A, delta B and delta C are small with respect to the length A, the width B and the height C, then we can neglect the terms second and third order in the change of the linear size of the cuboid. As a result, we can approximate the change delta V by minus the quantity of A times B times delta C, plus A times C times delta B, plus B times C times delta A. If we substitute this result in the equation derived for work, we find that the pressure volume work for compressing a substance in a rectangular cuboid can be approximated by minus the pressure P acting on the substance, times the change delta V in the volume of the substance due to the compression. We obtain the same result if we calculate the pressure volume work done on the surroundings by the expanding substance. The only difference between the two cases is that the change delta V in the formula is negative for compression and positive for expansion. We have seen that the pressure volume work done on a thermodynamic system by external pressure forces can be approximated with the product of the external pressure and the change of the volume of the system, provided its boundary is a rectangular cuboid in shape. We can also show that the pressure volume work has the same expression in the case of the compression of an ideal gas in a cylinder by a moving piston. However, in order to make the role of the external pressure more transparent, we will use a moving wall inside a closed cylinder instead of a cylinder with a piston. The space on the left-hand side of the wall is filled with an ideal gas and the space on the right-hand side contains any arbitrary substance, that can be a gas or a liquid. We consider the ideal gas enclosed in the space on the left-hand side as the thermodynamic system where the boundary consists of the wall of the cylinder and the moving wall. The space filled with the substance on the right-hand side and the environment of the cylinder belong to the surroundings of the system. While the ideal gas has the pressure P, the substance has the pressure Px representing external forces acting on the gas through the moving wall. If the pressure P is equal to the external pressure Px, the pressure forces are in balance on both sides of the wall and the wall stays at rest. If the external pressure Px is greater than that of the ideal gas, the external forces move the wall to the left, compressing the gas till the pressures become equal on both sides of the wall. Then the substance compressing the gas does work on the system, and its pressure volume work W can also be written as minus the pressure Px, times the change delta V in the volume of the ideal gas. In this example, delta V is simply equal to the cross-sectional area A of the cylinder, times the distance delta S covered by the moving wall. However, it can also be proved that the pressure volume work formula holds for any system with an arbitrary shape. If the pressure P in the system is smaller than the external pressure Px in its surroundings, the external pressure forces will compress the substance in the system. Even if the change delta V in the volume of the substance has any irregular shape, it can be approximated with a fine spatial mesh of rectangular cuboids, which allows us to prove the pressure volume formula. In many cases we study infinitesimal changes in thermodynamic processes as well, for example the infinitesimal change dV in the volume of a system. For an infinitesimal compression of a gas, the infinitesimal pressure volume work dW is precisely equal to minus the external pressure Px, times the infinitesimal change dV in the volume of the system. Then we have found that the infinitesimal pressure volume work dW done on a thermodynamic system by its surrounding with the external pressure P can be written as minus the external pressure P, times the infinitesimal change dV in the volume of the system. We will omit the subscript x from the external pressure, since the pressure P in the expression of the pressure volume work is always the pressure of the substance doing the work. In the example we used here, this substance belongs to the surroundings compressing the ideal gas in the system, but in other cases the gas in the system may be the working substance doing the pressure volume work on the surroundings during its expansion. By taking these two possibilities into account, we can state the following. If the external pressure forces compress a gas, then its volume decreases and the infinitesimal change dV in the volume is negative. As a result, the infinitesimal pressure volume work dW done on the gas by the external pressure forces is positive, since the surroundings transfers energy to the system in the form of pressure volume work. If a gas with the pressure P expands, its volume increases and the infinitesimal change dV in the volume is positive. Then the infinitesimal pressure volume work dW done on the surroundings by the expanding gas is negative, since the gas in the system transfers energy to the surroundings in the form of pressure volume work. This equation only describes the infinitesimal work of the pressure forces. In practice, we also want to determine the total pressure volume work of a complete thermodynamic process, where an ideal gas with the initial volume V1 is compressed so that it will occupy the volume V2 in its final state. Formally, we can integrate the differentials in both sides of the equation describing the differential pressure volume work. Then the total pressure volume work W done on the system can be written as minus the integral of the external pressure P over the volume V of the system between the initial volume V1 and the final volume V2 of the system. Here we write the external pressure P as a function of the volume V of the thermodynamic system, that is, we suppose that the pressure of the substance representing the surroundings may depend on the volume of the system. That is the case in the example, where the wall separating the system from the surroundings is moving in a cylinder of a fixed volume. Since the volume of the substance representing the surroundings is equal to the total volume of the cylinder minus the volume of the ideal gas, and the pressure of the substance depends on its volume, the external pressure P depends on the instantaneous volume of the ideal gas. We have seen that the first law of thermodynamics states that the change delta U in the internal energy of a thermodynamic system, that is the difference between its internal energy U2 in the final state and its internal energy U1 in the initial state, is equal to the heat Q exchanged between the system and its surroundings, plus the work W done by or on the system. If the work W is the pressure volume work done by external pressure forces compressing the substance in the system, then the change delta U in the internal energy of the system is given by the heat Q, minus the integral of the external pressure P over the volume V of the system between its initial volume V1 and its final volume V2. When we discuss the work done during the contraction or the expansion of a gas, we implicitly assume that the external pressure exerted on the moving wall in the cylinder is greater or smaller than the pressure of the gas in the system, but this difference is infinitesimally small. This infinitesimal difference is enough to move the wall by the net force of the unbalanced pressure forces acting on its both sides. For if the external pressure was much greater or smaller than that of the gas in the system, the movable wall could move fast enough to generate flows and whirls in the contracting or expanding gas. As a result, the sudden change in the volume of the gas would disturb the stationary state of the gas, that is the equilibrium of the thermodynamic system. Therefore, the thermodynamic states which the system is passing through while it is taken from its initial state to its final one, cannot be considered as equilibrium states. However, the equation of state for ideal gas only describes its behavior in equilibrium, and it is not clear at all what the functional relationship is between the state variables of an ideal gas in such a process, and how to describe the evolution of a non-equilibrium system in the state space. We also assume that the temperature of a thermal reservoir or a heat bath and that of a thermodynamic system in contact with the heat bath are almost the same for similar reasons. If the difference between the temperature THB of the heat bath and the temperature T of the substance in the system is infinitesimal, whether we warm or cool the system, then the thermal gradient between the system and its surroundings is small enough to produce any convective flow in the gas disturbing its equilibrium. If these conditions hold, then the changes in the thermodynamic state of a system are infinitely slow, and all the states which the system passes through are equilibrium states. In other words, the system maintains equilibrium during the infinitely slow thermodynamic process. It evolves through a series of equilibrium or static states, in which the equation of state can be applied. Such a thermodynamic process is called quasi-static process, where each state has only an infinitesimal deviation from the previous one during the infinitely long course between the initial and the final states of the system. In equilibrium, a thermodynamic system has well-defined values of macroscopic properties such as the temperature and the pressure of the system at each instant of the process. Therefore, a quasi-static process is represented by a well-defined path in the state space of the system. The equation of state can also be used to determine the functional relationship between the state variables describing macroscopic properties along the path of the equilibrium states. The path of a quasi-static process always lies on the surface determined by the equation of state in the state space. Here the equation stating that fx is equal to 0 represents an arbitrary equation of state, which depends on the state vector x of the system. This equation determines an n-1 dimensional hypersurface in the n-dimensional state space. Because the initial state 1 and the final state 2 of the thermodynamic process are equilibrium states and the equation of states holds in equilibrium, the states 1 and 2 are on the surface. In a quasi-static process, the series of states connecting the initial and the final states are also equilibrium states and they are also on the surface. Any finite difference between the state variables in two different states can be connected such a series of states on the surface, which have infinitesimal differences in their state variables. Quasi-static processes are idealized processes occurring infinitely slowly such that equilibrium holds at all times, but in practice such processes can be done slowly enough that the system remains at thermodynamic equilibrium at each instant, while it changes over a finite time. Since quasi-static processes cannot be completely realized for any finite change of the system, all processes in nature are non-quasi-static. However, we can study many different thermodynamic processes by approximating them as a quasi-static one, and draw important conclusions on their nature. We have already mentioned that in quasi-static processes the internal pressure and the external pressure are essentially the same on both sides of the moving wall separating the system from the surroundings. In other words, the external and internal pressure forces are equal in magnitude and opposite in direction. Then the work W done on the system by the external pressure forces is equal to minus the work W prime done on the surroundings by the internal ones. Therefore, the first law can also be formulated with the equation stating that the heat Q exchanged between a thermodynamic system and the surroundings is equal to the difference between the internal energy U2 in its final state and the internal energy U1 in its initial state, plus the work W prime done by the internal pressure forces. Explicitly, the heat Q is given by U2 minus U1, plus the integral of the internal pressure P over the volume V of the system from its initial volume V1 and its final volume V2. We can state that some amount of the heat absorbed by the system increases its internal energy, and the rest of the heat is used to expand the system and do pressure volume work on the surroundings. If there is no heat exchange between the system and the surroundings separated by an adiabatic wall, then the equation reduces to the form where the change delta U in the internal energy of the system is equal to the pressure volume work W done on the system, or minus the pressure work W prime done by the system. In both the cases, the mechanical work is given by minus the integral of the pressure P of the working substance over the volume between the initial volume V1 and the final volume V2 of the system. Since we talk about a quasi-static process, the pressure of the working substance in the surroundings and the pressure of the gas in the system remain equal during the process. As a result, the pressure P in both the integrals is equal to the gas pressure, which is a positive semi-definite function of the volume V of the gas. If an ideal gas is compressed and its initial volume is greater than its final volume, the value of the definite integral of the pressure with respect to the volume is negative. Then the change in the internal energy of the gas is positive, as we expect since the work is done on the gas. If the ideal gas expands and its initial volume is smaller than its final volume, the value of the definite integral of the pressure with respect to the volume is positive. Then the change in the internal energy of the gas is negative, as we expect since the work is done by the gas. We have seen that processes undergoing in thermodynamic systems can be represented by paths connecting the initial and the final states of the system in the state space. There is a special case of thermodynamic processes, where the initial and the final states of the system are the same. A process that eventually returns a system to its initial state is called a cyclic process. In the end of the process all the state variables, that is the macroscopic properties of the system, have the same value which they had in the initial state. As a result, the path of a cyclic process is a closed path in the state space. In the n-dimensional state space of a thermodynamic system, the point P represents the initial state of the system, and the closed path labeled by calligraphic P indicates that the system leaves its initial state and returns to it. The concept of cyclic process can be generalized to a connected sequence of thermodynamic processes, where the initial state of the first process and the sequence is the same as the final state of the last process in the sequence. Such a sequence of thermodynamic processes is known as thermodynamic cycle. Here we can see three distinct thermodynamic states represented by the points P1, P2 and P3 in the n-dimensional state space, which are connected with the path calligraphic P. The point P1 denotes the initial and the final state of the system, and the states P2 and P3 are the intermediate states in the thermodynamic cycle. A typical thermodynamic cycle consists of a succession of thermodynamic processes exchanging heat and work between the system and the surroundings, while varying state variables such as pressure, volume and temperature, and eventually returning the system to its initial state. In the thermodynamic cycle, the working substance in the system acts as means of transformation of energy into work. This cycle is important as it allows for the continuous operation, where heat is converted into work or vice versa by repeating the cycle. Such repeated thermodynamic cycles can be seen in the case of a moving piston in engines or the expansion and the compression of the working fluid in refrigerators. Two primary classes of thermodynamic cycles are power cycles and refrigeration cycles. Power cycles are cycles receiving heat as input energy and producing work as output energy, in other words converting heat into work. Therefore power cycles are also called heat engine. Refrigeration cycles transfer heat from low to high temperatures using work input, in other words they convert work into heat, and are also called heat pump. Thermodynamic cycles can be categorized in yet another way, as closed and open cycles. In closed thermodynamic cycles, the working substance returns to its original condition at the end of the cycle and it is recirculated in its final state, which is the same as its initial state at the beginning of the next cycle. For example, the working fluid in refrigerators and air conditioners is driven around a closed thermodynamic cycle between a heat source and a heat sink held at different temperatures. In open cycles, the working substance is renewed at the end of each cycle instead of being recirculated. For example, in internal combustion engines, gases produced in the combustion are exhausted and replaced by fresh air fuel mixture at the end of each cycle. We have seen that the internal energy of a thermodynamic system is a state function, that is a unique function of the thermodynamic state. If the state of the system is described by the state vector x in the n-dimensional state space, then the internal energy U can be evaluated at the state vector x. Since the initial and the final states of a system operating in a thermodynamic cycle are the same, the internal energy of the system is the same both at the beginning and the end of the cycle. If the state of the system is described by the state vector x at the beginning of the cycle, the system leaves this initial state evolving along the path calligraphic p and returns to the state x at the end of the cycle. Although the internal energy of the system can change in the intermediate states along the path, it will have its initial value at the end of the cycle. As a result, the change delta U in the internal energy is zero, and the first law can be formulated as the equation stating that the sum of the heat Q exchanged between the system and the surroundings, and the work W done on the system by the surroundings vanishes in a thermodynamic cycle. The first law can also be formulated by stating that the heat Q absorbed by the system is equal to the work W' done by the system performing a thermodynamic cycle. As we have seen, the operation of a heat engine is a typical example for a thermodynamic cycle, where heat is converted into mechanical work. The first law applied for a thermodynamic cycle can describe the energy balance in such a conversion performed by heat engines. However, in the operation cycle of a heat engine, not all the heat can be turned into work because some heat must also be released. This schematic diagram shows the exchange of energy in the thermodynamic cycle of a heat engine, where the engine is a part of the theoretical model describing the conversion of heat to work. In the diagram we can see a high-temperature reservoir or a hot source delivering the heat QH to the heat engine. The heat engine converts the delivered heat to the mechanical work W', and releases the heat QC, which is absorbed by a low-temperature reservoir or a cold sink. The heat absorbed by the sink is considered as a loss of the energy delivered to the heat engine, since it is not converted to mechanical work. Although we used finite amounts of internal energy, heat, and work to formulate the first law of thermodynamics, the law can also be written in differential form. If dQ is the infinitesimal amount of heat absorbed by a thermodynamic system and dW is the infinitesimal work done on the system, then the infinitesimal change du in the internal energy of the system is equal to dQ plus dW. In the case of the pressure volume work done on a gas with the pressure P and the infinitesimal change dV in its volume, the change du in the internal energy of the gas is given by dQ minus P times dV. Similarly, we can write that the infinitesimal heat dQ absorbed by the system is equal to the infinitesimal change du in its internal energy, plus the infinitesimal work dW' done by the system, where the work dW' done by an expanding gas can be written as P times dV. In order to study an infinitesimal amount of internal energy of a thermodynamic system, that is the differential of U as a function of the state vector of the system, we consider a general case. Let F be a function defined over the n-dimensional state space of a thermodynamic system, that is let F be a state function. This means that the value of F is determined if we specify the state vector x in the state space. Let us evaluate this function at another state, which is at an infinitesimally small distance from the original state in the state space. Then this state can be written as the state vector x plus the infinitesimal distance vector dx. We can say that we transform the initial state described by the state variables x1, x2, ellipsis, xn, to the final state described by the state variables x1 plus dx1, x2 plus dx2, ellipsis, xn plus dxn. Now we can write the differential of the function f as the difference between the function f evaluated at the state vector x plus the difference vector dx, and the function f evaluated at the state vector x. If the function f is differentiable with respect to the state variables, then this expression is the exact differential of the function f corresponding to the passage from the initial state to the final state. The exact differential of f can be written as the sum of the partial derivative of f with respect to the state variable xi with all the other state variables kept fixed, times the differential of xi, where the index I runs form 1 to n. If a thermodynamic system evolves from its initial state 1 to its final state 2, then we can determine the difference delta f in the function f evaluated at the state vector x2 in its final state and at the state vector x1 in its initial state. We can also obtain this difference by integrating the differential of the function f along the path representing the thermodynamic process of the system in the state space. If we substitute the exact differential of the function f into the path integral, then the difference delta f can be written as the sum of the integrals of the partial derivatives of the function f with respect to the state variables over the same state variables from the state 1 to the state 2. Since the difference in the function f depends only on the initial and the final states of the system, the integral and the sum of the integrals can only depend on these states and cannot depend on the path of the integration. If we choose another path connecting the states 1 and 2 in the state space, that is, we let the system evolve from its initial state to its final state in another thermodynamic process, the difference delta f in the state function f still is the same as the one obtained in the original process. Since the function f is an arbitrary state function, these findings also hold for the internal energy of a thermodynamic system. Then the fact that the internal energy U is a state function but the heat Q and work W are not, can be expressed mathematically by stating that the differential dU is an exact differential, while the infinitesimal quantities dQ and dW are inexact differentials. As a result, the first law of thermodynamics can be formulated as follows. The sum of the infinitesimal amount of heat absorbed by a thermodynamic system and the infinitesimal work done on the system is an exact differential, that is the exact differential of the internal energy of the system. Then dU is equal to delta Q plus delta W, where dU denotes the exact differential of the internal energy, and delta Q and delta W denote the inexact differentials of heat and work respectively. We can also write that delta Q is equal to dU plus delta W prime, where delta W prime is the infinitesimal work done by the system. We normally use the notation delta for an infinitesimal quantity to emphasize that it is an inexact differential, otherwise we just denote any infinitesimal difference with d. In the context of thermodynamics we already know that the internal energy is a state function and it has an exact differential, whereas heat and work are so-called path functions depending on the path of the thermodynamic process in the state space, and they have inexact differentials. If we keep this fact in mind, we can just use the notation d for any infinitesimal thermodynamic quantity throughout the lecture. We have already determined the work W prime done by an expanding gas. If the heat Q is absorbed by an ideal gas in the chamber of a cylinder sealed with the piston, then the gas evolves from its initial state with the pressure P1 and the volume V1 to its final state with the pressure P2 and the volume V2. The pressure volume work W prime done by the gas is equal to the integral of the changing gas pressure P over the volume V of the gas from the initial volume V1 to the final volume V2. If the gas is expanding, that is V2 is greater than V1, then the pressure volume work is positive. We can illustrate the expansion of the gas by plotting the pressure volume diagram of the gas, where the states 1 and 2 of the gas are connected with the path calligraphic P representing the process of expansion. Then the area of the plane figure with the corner points labeled by the letters V1, V2, 2, and 1 under the curve calligraphic P gives the pressure volume work done by the expanding gas. For another process represented by the path calligraphic P', where the change in the temperature of the gas is different during its expansion, the area under the curve calligraphic P will be different. As a result, the pressure volume work will also be different. This is another demonstration of the fact that the work done by the gas depends on both the states 1 and 2 in the path connecting these states. Now we determine the area under the curve calligraphic P. First we can compute the area of the rectangle O, V2, 2 and P2, which is equal to P2 times V2. Then we add the area of the plane figure with the corner points P1, P2, 2 and 1 to the area of the rectangle. This area is given by minus the integral of the volume V with respect to the pressure P from the pressure P1 to the pressure P2, which is positive since dP is negative for expansion. Finally we subtract the area of the rectangle O, V1, 1 and P1 from the sum, where the area is equal to P1 times V1. As a result, the pressure volume work W' done by the expanding gas can be written as P2 times V2, minus P1 times V1, minus the integral of the volume V of the gas with respect to the pressure P from the initial pressure P1 to the final pressure P2. In the original formula, we computed the pressure volume work W' by integrating the gas pressure with respect to the volume, which is a convenient method if the pressure is constant. Then we only need to multiply the constant pressure by the change delta V in the volume of the gas. In the new formula, we need to evaluate the integral of the volume with respect to the pressure, which does not seem to be a convenient method since the volume of the gas is changing for an expanding gas. However, the new formula helps us to introduce a new thermodynamic variable describing the state of a system if we apply the first law of thermodynamics. The first law states that the heat Q absorbed by the gas is equal to the change U2 minus U1 in the internal energy of the gas, plus the work W' done by the gas. Then we can write that the heat Q is equal to the quantity of U2 plus P2 times V2, minus the quantity of U1 plus P1 times V1, minus the integral of the volume V of the gas with respect to the pressure P from the pressure P1 to the pressure P2. By applying the equation obtained for the first law, we can introduce a new thermodynamic quantity called enthalpy. If a thermodynamic system is in a given state described by the state variables pressure P, volume V, temperature T and so on, we can also determine its internal energy U as a function of the given state variables. Then the enthalpy H of a substance in the system is defined by the internal energy U of the substance, plus the product of the pressure P and the volume V of the substance. We can see from its definition that enthalpy has the unit of energy, and its SI unit is Joule. Before applying this definition for the first law, we introduce another thermodynamic quantity called technical work done by the system in a thermodynamic process changing its pressure from the initial pressure P1 to the final pressure P2. The technical work W' tech is defined by minus the integral of the volume V of the substance in the system with respect to the pressure P of the substance from the pressure P1 to the pressure P2. By using the definition, we can also determine an infinitesimal amount of technical work done by the system, which is equal to minus the volume V times the infinitesimal change in the pressure P of the system. Now we can substitute these definitions into the first law for a system doing pressure-volume work. Here the first two terms in the right-hand side are the enthalpy of the system in its initial state 2 and its final state 1 respectively, whereas the last term is the technical work. Then the first law of thermodynamics states that some amount of the heat absorbed by the system increases the enthalpy of the system, and the rest of the heat is converted into technical work. That is, the heat Q absorbed by the system is equal to the difference H2 minus H1 of the enthalpy of the system, plus the technical work W' tech done by the system. If we keep the original form of the last term, we can write that the heat Q is given by the final enthalpy H2 minus the initial enthalpy H1, minus the integral of the volume V with respect to the pressure P from the initial pressure P1 to the final pressure P2. This form can also be used to write the first law in differential form stating that an infinitesimal change in the enthalpy H is equal to the infinitesimal amount of heat Q absorbed by the system, plus the pressure P of the system times the infinitesimal change in the volume V of the system. By definition, enthalpy is a state function. If the state of a thermodynamic system is given by the state vector x in the n-dimensional state space, then the internal energy U of the system is also given in that state as a unique function of the state vector x. This is the case for the enthalpy as well. Since the enthalpy H of the system is a unique function of the state of the system, we can determine it by fixing the state vector x. As a result, the differential of enthalpy in the first law is also an exact differential. It depends on the thermodynamic process which form of the first law expressed in the terms of internal energy or enthalpy is more applicable. In the case of isochoric processes where the volume of the thermodynamic system is constant, the infinitesimal change dV in the volume of the system vanishes. As a result, the second term in the right-hand side of the differential form of the first law expressed in the terms of the infinitesimal change in internal energy is equal to 0. By integrating the result, we find that the heat Q exchanged between the system and the surroundings is equal to U2 minus U1, that is the change in the internal energy of the system. In the case of isobaric processes where the pressure of the system is constant, the infinitesimal change dP in the pressure of the system vanishes. Then we can drop the second term in the right-hand side of the differential form of the first law expressed in the terms of the infinitesimal change in enthalpy. By integrating the result, we can see that the heat Q exchanged between the system and the surroundings is equal to H2 minus H1, that is the change in the enthalpy of the system. In other words, the heat absorbed by a system with a constant volume is equal to the increase in the internal energy of the system, whereas the absorbed heat is equal to the increase in the enthalpy of the system provided its pressure is constant. We can illustrate the importance of the technical work by considering the thermodynamic cycle in steam engines. The idealized cycle of a steam engine consists of 4 thermodynamic processes, where the working substance is a gas or vapor pushed and expanded by a moving piston in a cylinder. In the first process, the starting position of the piston is at the wall with the 2 valves of the cylinder. The intake valve is open and the exhaust valve is closed, which allows the gas to enter the cylinder with the constant pressure P1 and move the piston. When the chamber between the wall and the piston expands to a given volume V1, the intake valve closes, preventing the gas from entering the chamber. The work done by the gas is given by the product of the constant pressure P1 of the gas and the change V1 in its volume. In the second process, the chamber is closed but the gas expands and moves the piston, further increasing the volume of the chamber to the volume V2. Since the gas is not allowed to enter the chamber, the pressure of the gas drops to the pressure P2 during its expansion. Then the pressure volume work W' done by the expanding gas is equal to the integral of the gas pressure P with respect to its volume V from the volume V1 to the volume V2. In the third process, the exhaustion valve opens and the gas is pushed out by the piston at constant pressure, reducing its volume in the chamber to 0. Then the work done on the gas is given by the product of the constant pressure P2 and the change V2 in the volume of the chamber. That is, the work done by the gas is equal to minus P2 times V2. In the fourth process, the pressure can be equalized in the chamber and the surroundings by closing the exhaustion valve and opening the intake valve. Then the pressure of the gas will increase from the pressure P2 to the pressure P1 at the intake valve, while the volume of the chamber remains 0. Since there is no change in the volume, no work is done. In the 4 processes repeated in the cycle, the gas is the working substance while it enters and leaves the cylinder, changing its mass continuously. The work done by the steam engine is the technical work W' tech, which is given by P1 times V1, plus W' minus P2 times V2. This expression can be written as P1 times V1, minus P2 times V2, minus the integral of the pressure P with respect to the volume V from V1 to V2. By applying partial integration, we obtain minus the integral of the volume V with respect to the pressure P from P1 to P2. In the pressure volume diagram of the cycle, the 4 processes are represented by the sections from the point P1 to the point 1, from the point 1 to the point 2, from the point 2 to the point P2, and from the point P2 to the point P1, respectively. We can see that the technical work is equal to minus the integral of the volume V with respect to the pressure P from the pressure P1 to the pressure P2, which is the area of a plane figure with the corner points P1, P2, 2, and 1. In the process represented by the path between the points 1 and 2, the mass of the gas is constant and it absorbs the heat Q, increasing its enthalpy by H2 minus H1. The first law of thermodynamics on its own is not sufficient to establish the explicit dependence of the internal energy of a thermodynamic system on its state variables. If we want to derive such a functional relationship, then we need empirical data besides the theoretical considerations on the nature of the system. Now we will present an experiment on the free expansion of gases, which helps to determine such a relationship between the internal energy of an ideal gas and its state variables. The free expansion of air was first studied by Gay-Lussac in 1807, and Joule performed the improved version of his experiment in 1845. Here we can see the apparatus used by Joule. It consists of 2 identical gas containers, which are connected with a tube and placed into a vessel filled with water, serving as a calorimeter. The gas containers are denoted by the letters R and E in the figure. The tube is closed with the valve separating the 2 containers from each other. The container R is filled with air at a pressure of 20 atmosphere, whereas the container E is evacuated. Let V1 and P1 denote the volume of the identical containers and the initial pressure in the container R respectively. If we open the valve, then the gas will expand and fill the evacuated container. As a result, the expanding gas equalizes the pressure in the containers and reaches equilibrium. Then the volume V2 of the gas after its free expansion will be equal to 2 times its initial volume V1, while its pressure drops to 10 atmosphere. That is, the final pressure P2 of the gas will be the half of its initial pressure P1. When Joule performed the experiment, he carefully measured the change in the temperature of the water in the calorimeter. However, he was not able to detect any change of the water temperature, which indicated that the gas did not absorb any heat from the water. Therefore, the initial temperature T1 of the gas was equal to its final temperature T2 in contradiction with the expectation that the gas would cool off under expansion. We also note that the product of the pressure and the volume of the gas is the same before and after its expansion, that is, the initial pressure P1 of the gas times its initial volume V1, is equal to the final pressure P2 of the gas times its final volume V2. The expanding air in the containers can be considered as a given amount of ideal gas with a thermodynamic state determined by its pressure, volume and temperature. The relationship between the state variables of the gas is given by the ideal gas law stating that the pressure P of n mole gas times its volume V is equal to n times the gas constant R times the absolute temperature T of the gas. Now we can apply the first law of thermodynamics stating that the difference between the internal energy U2 of the gas in its final state and its internal energy U1 in its initial state is equal to the heat Q exchanged between the gas and the calorimeter, plus the work W done on the gas. Since no heat exchange was measured and the external forces did not do work on the gas filled in the containers with fixed walls, the heat Q and the work W are zero. Therefore the first law states that the internal energy of the gas is the same in its initial and final states, that is U1 is equal to U2. In the experiment, Joule demonstrated that the temperature of the gas is the same before and after the free expansion, while it doubles its volume and halves its pressure. Since the internal energy U of the gas is the same in the initial and the final states of the experiment, it cannot depend on its pressure and volume. Only the product of the pressure and the volume is the same before and after the expansion, which would allow us to express the internal energy as a function of the pressure times the volume, and the temperature. However, this product is directly proportional to the temperature, as the ideal gas law shows. Then we can express the internal energy as a function of temperature, which neither depends on the pressure nor the volume. The conclusion drawn from the result of the experiment is the following. The internal energy of an ideal gas depends only on one state variable, which is the absolute temperature of the gas. In other words, the internal energy U of an ideal gas is a unique function of its absolute temperature T. Let us discuss the consequences of this important result for an ideal gas undergoing change in isochoric and isobaric processes. First we consider an isochoric process, where an infinitesimal amount of heat is transferred to a given amount of gas in a constant volume, and the infinitesimal change in the volume of the gas is zero. We have already seen that the differential form of the first law of thermodynamics states that the infinitesimal amount dQ of heat delivered to the gas is equal to the infinitesimal change du in the internal energy of the gas, minus the pressure P of the gas times the infinitesimal change dV of its volume. In an isochoric process this equation reduces to the equality of dQ and du. The specific heat capacity CV of an ideal gas measured in an isochoric process is defined by 1 over the mass m of the gas, times the derivative of the heat Q absorbed by the gas with respect to its absolute temperature T for a constant volume. By substituting the first law into this definition, we obtain the following differential equation. The derivative of the internal energy U of the gas with respect to its absolute temperature T is equal to the mass m of the gas, times its specific heat capacity CV measured in an isochoric process. Here both the internal energy and the specific heat capacity depend only on the temperature. If the explicit dependence of the specific heat capacity on the temperature is given, we can write the internal energy of the gas as a function of temperature by integrating the differential equation. According to the measurements, the specific heat capacity of gases in a constant volume is independent of their temperature, at least in a wide temperature range. Then we will assume that the specific heat capacity CV of an ideal gas measured in a constant volume is constant. By integrating the differential equation we obtain the following solution. The internal energy U of the gas is equal to the mass m of the gas, times its specific heat capacity CV for a constant volume, times its absolute temperature T, plus an integration constant U0. This integration constant is the zero-point energy of the gas, that is the internal energy of the gas at absolute zero temperature. In classical thermodynamics the zero-point energy can be chosen to be zero, since the first law and its applications involve only differences in energy, and U0 always cancels out. Then we can conclude that the internal energy U of an ideal gas with the given mass m at the absolute temperature T is equal to the mass m, times the specific heat capacity CV of the gas measured in isochoric processes, times the temperature T, that is the internal energy of an ideal gas is directly proportional to its absolute temperature. We can also deliver an infinitesimal amount of heat to an ideal gas in an isobaric process, that is for constant pressure, where the infinitesimal change dP in the gas pressure is zero. Now we can use the first law of thermodynamics expressed in the terms of enthalpy, stating that the differential of the heat Q is equal to the differential of the enthalpy H of the gas, minus the volume V of the gas times the differential of its pressure P. Since we can drop the second term in the right-hand side for isobaric processes, we see that the infinitesimal heat dQ absorbed by the gas is equal to the differential of the enthalpy H of the gas. The specific heat capacity Cp of the gas measured in isobaric processes is defined by 1 over the mass m of the gas, times the derivative of the heat Q absorbed by the gas with respect to its absolute temperature T for a constant pressure. By substituting this result into the first law, we obtain a differential equation for the enthalpy of the gas. That is the derivative of the enthalpy H of the gas with respect to its absolute temperature T is equal to the mass m of the gas, times its specific heat capacity Cp measured in isobaric processes. Although the specific heat capacity of gases at constant pressure depends on the temperature of the gas, it can be considered constant for a wide range of temperature. Therefore, the integration of the differential equation gives the solution for the enthalpy of the gas, which is equal to the mass m, times the specific heat capacity Cp for a constant pressure, times the temperature T, plus an integration constant H0. This constant is the enthalpy of the gas at absolute zero, which can be set to zero. Then we can write that the enthalpy of an ideal gas with the mass m at the absolute temperature T is equal to the mass m, times its specific heat capacity Cp measured in isobaric processes, times the absolute temperature T, that is the enthalpy of an ideal gas is directly proportional to its absolute temperature. The functional relationships derived between the internal energy and the enthalpy of an ideal gas and its temperature are also known as the caloric equation of state for an ideal gas. The first caloric equation of state of an ideal gas for a given mass m at the absolute temperature T states that the internal energy U of the gas is equal to the mass m, times the specific heat capacity Cv of the gas for a constant volume, times the temperature T, which is equal to the heat capacity Cv of the given amount of gas for a constant volume, times the temperature T. In the second caloric equation of state, the enthalpy H of the gas is given by the mass m, times the specific heat capacity Cp of the gas for a constant pressure, times the temperature T, which is equal to the heat capacity Cp of the given amount of gas for a constant pressure, times the temperature T. If we divide these equations by the mass m of the gas, then we can write them as follows. The specific internal energy u of an ideal gas is equal to its specific heat capacity Cv for a constant volume, times the absolute temperature T. The specific enthalpy h of an ideal gas is equal to its specific heat capacity Cp for a constant pressure, times the absolute temperature T. Here the specific internal energy u of a substance is simply defined as the ratio of its internal energy U to its mass m, which has the unit joule per kilogram. Similarly, the specific enthalpy h of a substance is simply defined as the ratio of its enthalpy H to its mass m with the unit of joule per kilogram. Since the enthalpy of a gas is defined by the sum of the internal energy and the product of the pressure of the gas and its volume, the product of the pressure and the volume is just the difference between the enthalpy and the internal energy. Then we can combine the caloric equations of state of an ideal gas by writing that the pressure P times the volume V given by the enthalpy H minus the internal energy U is equal to the mass m, times the specific heat capacity Cp for a constant pressure, times the absolute temperature T, minus the mass m, times the specific heat capacity Cv for a constant volume, times the absolute temperature T. If we factor out the mass and the temperature in the right-hand side, then we obtain that P times V is equal to the m times the difference of Cp and Cv, times T. Now we can apply the ideal gas law for a given amount of gas, which states that the pressure P of the gas times its volume V is equal to the amount N of the substance, times the gas constant R, times its absolute temperature T. The right-hand side can also be written as the mass m of the gas, times its specific gas constant Rs, times its absolute temperature T. The specific gas constant Rs of the gas is given by the ratio of the universal gas constant R to the molar mass m sub m of the gas, which is equal to the amount N of substance times the gas constant, divided by the mass m of the substance. Then we can write that the mass m times the difference between Cp and Cv, times the temperature T is equal to the mass m, times the specific gas constant Rs, times the temperature T. This expression reduces to a relation stating that the difference of Cp and Cv is equal to Rs, which is Meyer's relation. We have already derived this relation in another form, which we can see if we express the mass m times the difference between Cp and Cv times the temperature T, as the amount n of the substance, times the gas constant R, times the temperature T. This gives an expression stating that the difference of the heat capacities Cp and Cv of the substance is equal to n times R. If we divide this result by the amount n of the substance, then we regain Meyer's relation from the caloric equation of state for an ideal gas and the ideal gas law. As a result, this relation can be written in two alternative forms. The first one states that the difference between the specific heat capacity Cp for a constant pressure, and the specific heat capacity Cv for a constant volume is equal to the specific gas constant Rs of the gas. In its second form, Meyer's relation tells us that the difference between the molar heat capacity C sub Pm for a constant pressure, and the molar heat capacity C sub Vm for a constant volume is equal to the universal gas constant R. We can also determine the internal energy of an arbitrary homogeneous and isotropic body as a function of its thermodynamic parameters. The state variables of such bodies are the pressure exerted on the body by an external force, the volume of the body and its temperature. The equation of state for the body provides a functional relation between these state variables. As in the case of an ideal gas, one of the state variables can be expressed in the terms of the other two variables by solving the equation of state for it. Then we are able to reduce the number of independent variables describing the thermodynamic state of the body. We can write the pressure as a function of the volume and the temperature of the body, we can express its volume in the terms of the pressure exerted on it and its temperature, or we can give the temperature of the body as a function of the pressure and its volume. As a result, the internal energy of the body, which is a state function, depends on only two independent state variables. In other words, the internal energy U can be expressed as a unique function of the volume V and the temperature T, the pressure P and the temperature T, or the pressure P and the volume V. For an isochoric process, where the heat absorbed by the body increases its internal energy, that is dQ is equal to du, we could write the specific heat capacity Cv of the substance as the mass m of the body, times the derivative of the internal energy U of the body with respect to its absolute temperature T for a constant volume. Similarly, for an isobaric process, where the heat absorbed by the body increases its enthalpy, that is dQ is equal to dH, we could write the specific heat capacity Cp of the substance as the mass m of the body, times the derivative of the enthalpy H of the body with respect to its absolute temperature T for a constant pressure. Since an infinitesimal change in the enthalpy H at a constant pressure is equal to the infinitesimal amount of heat Q, that can be written as the mass m of the body, times the specific heat capacity Cp of the body measured at constant pressure, times the infinitesimal change in the absolute temperature T of the body. We can also apply the definition of enthalpy to derive its infinitesimal change in isobaric processes, and write it as the differential of the internal energy U, plus the pressure P times the differential of the volume V. If we combine these two equations, then we obtain an expression stating that the partial derivative of the internal energy U of the body with respect to its absolute temperature T for a constant pressure is equal to the mass of the body, times its specific heat capacity Cp for constant pressure, minus the pressure P times the derivative of the volume V of the body with respect to the absolute temperature T for a constant pressure. At the same time, we can also differentiate the internal energy U as a function of the volume V and the absolute temperature T with respect to the temperature for a constant pressure. Then its partial derivative can be written as the partial derivative of the internal energy U with respect to the volume V for a constant temperature, times the partial derivative of the volume V with respect to the absolute temperature T for a constant pressure, plus the partial derivative of the internal energy U with respect to the absolute temperature T for a constant pressure. In the first term, we use the chain rule of the derivative of the composition of the functions U and V. Since the left-hand side of these equations are the same, we can combine them into one expression. As a result, we can state that the mass m times the specific heat capacity Cp, minus the pressure P times the derivative of the volume V with respect to the absolute temperature T for a constant pressure, is equal to the partial derivative of the internal energy U with respect to the volume V for a constant temperature, times the partial derivative of the volume V with respect to the absolute temperature T for a constant pressure, plus the mass m times the heat capacity Cv. Here we substituted the expression of the heat capacity Cv obtained for a constant volume into the last term in the right-hand side of the equation. If we regroup the terms and divide the result by the mass m, we obtain a relation between the specific heat capacities of a homogeneous isotropic body, which is the following. The difference between the specific heat capacity Cp of the body for a constant pressure and its specific heat capacity Cv for a constant volume is equal to 1 over the mass m of the body, times the sum of the partial derivative of the internal energy U of the body with respect to its volume V for a constant temperature and the pressure P, times the partial derivative of the volume V with respect to the absolute temperature T of the body for a constant pressure. This general relation links such properties of the body with each other that can be measured in different thermodynamic processes. In an isothermal process that is at constant temperature, there is a unique relation between the internal energy of the body and its volume. In a general case, any change in its volume also causes some change in its internal energy, which can be described by the partial derivative of the internal energy U with respect to the volume V at a constant temperature. In an isobaric process, we can measure the specific heat capacity Cp of the body as a function of temperature, and determine the change in its volume as a function of its temperature. The partial derivative of the volume V with respect to the absolute temperature T for a constant pressure gives a quantitative description of this function. In an isochoric process, we can measure the specific heat capacity Cv of the body as a function of temperature. Since this relation is a general description of the thermodynamic properties of a homogeneous and isotropic substance, we can consider a given amount of ideal gas as its special case. The ideal gas law states that the pressure P of the gas times its volume V is equal to its mass m, times its specific gas constant Rs, times its absolute temperature T. Then the volume of the gas is just directly proportional to its absolute temperature for a constant pressure, where the proportionality constant is equal to the mass m times the specific gas constant Rs, divided by the pressure P. The internal energy U of an ideal gas is given by the mass m of the gas, times its specific heat capacity Cv for a constant volume, times its absolute temperature T. This equation shows that the internal energy of the gas does not depend on its volume. If we use these results to determine the partial derivatives in the relation, we obtain the following. The partial derivative of the internal energy U of an ideal gas with respect to its volume V for a constant volume vanishes, whereas the partial derivative of the volume V of the gas with respect to its absolute temperature T for a constant pressure is equal to the proportionality factor m times Rs divided by P. The specific gas constant Rs is equal to the universal gas constant R divided by the molar mass m sub m of the gas. By substituting these expressions into the relation, we obtain Meyer's relation, as expected. That is the difference between the specific heat capacity Cp of the body for a constant pressure and its specific heat capacity Cv for a constant volume is equal to the universal gas constant R divided by the molar mass m sub m of the gas. We can interpret the general relation between the specific heat capacity Cp and Cv as follows. If the equation of state of the body is given, that is its pressure P as a function of its volume V and its absolute temperature T is known, then the volume V can also be expressed as the function of the pressure P and the absolute temperature T. It allows us to determine the partial derivative of the volume V with respect to the temperature T for isobaric processes. Furthermore, we need some data obtained from measurements to evaluate this relation. The specific heat capacity Cp and Cv as functions of the volume V and the temperature T are measured for different types of materials in experiments. Such data can be used for the homogeneous and isotropic body made of a given material. For isochoric processes, the heat capacity Cv of the body determines the partial derivative of its internal energy U with respect to the absolute temperature T. The partial derivative of the internal energy U with respect to the volume V for a constant temperature can also be computed by substituting the specific heat capacities and the partial derivative of the volume with respect to the temperature for a constant pressure into the relation. Now we have all the information to determine the internal energy of the body. The total differential of the internal energy U as a function of the volume V and the absolute temperature T can be written as the partial derivative of the internal energy with respect to the volume for a constant temperature times the differential of the volume, plus the partial derivative of the internal energy with respect to the temperature for a constant volume times the differential of the temperature. Since we have determined the partial derivatives in this expression, the differential is also determined. By integrating this expression, we obtain the internal energy of the body as a function of its volume and its absolute temperature. In the end of this presentation on the first law of thermodynamics, we will give a summary of the topics discussed here. We started with the clarification of the concept of heat and its relation to the thermal state of bodies. By considering the results of experiments with bodies or substances brought into thermal contact, We found that the heat exchanged between them is directly proportional to the mass of the bodies and the change in their temperature. We could also establish that heat is conserved during its exchange between bodies. We defined the unit of heat called calorie, and we enlisted several different precise definitions for calorie, since the thermal properties of water used to define this unit depend on its temperature. We also saw that the thermal properties of different substances can be described by the specific heat capacity or the specific heat of a given amount of matter. In the discussion on calorimetry measuring the amount of heat released or absorbed during a chemical reaction or a physical process, we presented different methods and devices designed to measure the transport of heat in such processes. Then we considered various physical processes like friction, which could help us to recognize that heat is a form of energy, and it can be converted into mechanical work and vice versa. We also saw that this assumption opened the door for the kinetic theory of heat, superseding its caloric theory. We introduced the concept of the mechanical equivalent of heat describing the rate of the conversion of heat to mechanical work in thermodynamic processes. We also presented the paddle wheel experiment, where Joule was able to measure the mechanical equivalent of heat. In another experiment with a given amount of ideal gas heated at constant volume and then at constant pressure, we demonstrated that the definition of the mechanical equivalent of heat gives Meyer's relation, provided we choose the unit of work as the unit of heat. We introduced some fundamental concepts of thermodynamics, such as thermodynamic system, boundary and surroundings. We also categorized systems based on their composition, and classified boundaries based on their properties related to the transport of mass, momentum and energy. We built a state space of a thermodynamic system from its state variables describing its thermodynamic state. We showed how to represent a stationary state of a system in such a state space, and we defined thermodynamic equilibrium as well. That also helped us to represent the equation of state in the state space of a thermodynamic system. After a short historical overview on the development on its idea, we introduced the first law of thermodynamics formulating the conservation of energy. The law states that energy can neither be created nor destroyed but can only transform from one form to other forms. We rephrased this statement for thermodynamic systems, saying that the total energy of an isolated system is conserved. In the case of non-isolated systems, the transport of mass, energy and momentum is allowed through their boundaries. Then the first law also states that the change in the total energy of a non-isolated system is equal to the sum of all heat transported to or from, and the work done by or on the system. By applying the kinetic theory of heat, instead of using the total energy of a thermodynamic system, we could formulate the law with the internal energy of a thermodynamic system at rest instead its total energy, since we only need to consider the microscopic motion in the system. We concluded that internal energy is a state function, that is completely determined by the thermodynamic state of the system. We also saw an important consequence of the conservation of energy in any transport process. A perpetuum mobile of the first kind cannot exist. We also defined the concept of quasi-static thermodynamic process as a series of equilibrium states, where each equilibrium state has only an infinitesimal deviation from the previous one during the infinitely long course between the initial and the final states of the system. Since the state variables describing the state of the system are well defined in such a process, the equation of state holds for the state variables of the system throughout the quasi-static process. This approximation allowed us to simplify our analysis on the pressure-volume work done in thermodynamic process, when we applied it in the first law. We also introduced the concept of thermodynamic cycle as a connected sequence of processes, where the initial state of the first process and the sequence is the same as the final state of the last process in the sequence. Since internal energy is state function, the first law of thermodynamics states that the heat absorbed by a system is equal to the work done by the system in a thermodynamic cycle. Thermodynamic cycles also help us to interpret the differential form of the first law, where we recognize that the differential of internal energy is an exact differential, whereas the differentials of heat and work are inexact differentials. We could apply the first law of thermodynamics with the explicit formula of the pressure-volume work to calculate the technical work of a steam engine, and introduce the enthalpy of a thermodynamic system, which is a state function. We finished the presentation with another application of the first law of thermodynamics, namely Joule's experiment studying the free expansion of an ideal gas. We saw that no heat exchange was measured between the gas and its environment in this experiment. Based on both the law of conservation of energy and the ideal gas law, we could establish that the internal energy of the ideal gas only depends on its absolute temperature. We investigated this relation for both isochoric and isobaric processes, where the two versions of this relation were interpreted as the caloric equations of state for an ideal gas. We could also derive a relation between the internal energy and the state variables of homogeneous isotropic bodies, which is a generalization of the formulae obtained for an ideal gas, and it allowed us to determine the internal energy of the system by measuring its thermodynamic variables in a given state.